along that line. Yeah, so let me introduce the first speaker. Let me pull out my notes. So I guess, Geddes actually, we met a few years ago when we interned together at Meta AI at that time. And right now he's assistant professor in the Department of Computer Science at the University of North Carolina, Chapel Hill. He has been working on video understanding, action recognition, multimodal learning, and have proposed a lot of well-known models like Transformer. I guess many of us have used that, Max Pro, and his work on video understanding received the best paper nomination at CVPR 20, and recently has also conducted many works about video model architecture design for long-form video understanding, like video transformer models. So besides that, he also did quite some interesting work on basketball analysis, and hopefully that can also involve some long-form video understanding technologies. And let's, without further ado, welcome Geddes to give his talk on long-form.
Thank you. Thank you, Mike. Yes, really great to be here. Thank you for inviting me. So today I'll talk about some of our work on evaluating and benchmarking long-range video understanding models. And before I start talking about long-form video modeling, I also wanted to talk just a little bit about short-range models. And so, as all of you are probably aware, most modern video recognition models these days are actually short range. So they're optimized on very short video clips, typically 5 to 10 seconds in duration. And then afterwards, they're usually evaluated on some standard action recognition or video classification benchmarks, the most popular, which is probably the kinetics benchmark, consisting of roughly 240,000 videos lasting for roughly 5 to 10 seconds and spanning 400 action categories. And so while these benchmarks and evaluation protocols for short range video models are well established, so meaning that, if I was to come up with a new short range video model, I would be expected to evaluate it on some video classification benchmark like kinetics. I argue that this is not the case for long range video modeling. And so what do I mean by that? Well, so what I mean by that is that, well, for one, it's not clear what are really the good tasks that we should evaluate these long-range video models on, and it's also not clear what kind of benchmarks would best stress test this long-range modeling ability. And so I think this is a big problem because we all know how much these strong benchmarks drive progress in computer vision. So we all know ImageNet and kinetics, how much they contributed to the development of image and video understanding models. So I think we need to have something similar like that, really rigorous evaluation benchmark for long-range video modeling. And so that's what I'll focus on in my today's talk, basically, how we should evaluate these long-range video models. And so here's the outline of the talk. So initially, what I'll do, I'll briefly talk about some of our early efforts on long-form video modeling, and also some of our experience with the existing long-form video benchmarks. So those are going to be the first 2 points in the outline. And then I'll finish up the talk with some of our ongoing work and some of our plans on developing a new long-range video evaluation benchmark. So let me start with this first bullet point on long-range video classification. So just for a little bit of context, I really got interested in long-form video modeling a couple of years ago when I was working with this Transformer model. And so the story was that we developed this scalable divided space-time attention, and basically what we found out is that it enabled us to apply our model on much longer videos compared to previously established 3D CNN models. And so that's kind of this interesting capability is what pushed me to explore more into this long-form video understanding. But unfortunately, at the time, there were no benchmarks to evaluate these long-form video models on. So what we did instead is we created our own benchmark using the existing How to 100 million data set. And for those of you who are unfamiliar with how to 100 million, so it's a large-scale instructional video data set consisting of roughly 1 million videos that are showing people performing a wide array of different tasks like making breakfast, cleaning a house, repairing a car, assembling some furniture, and so on. And the good thing for our purposes about this data set is that on average, each of these videos lasts for roughly 7 minutes. So orders of magnitude longer than the existing video benchmarks. And another nice thing was that each video also has a label indicating what of the tasks the human is performing in that video. And so we can use these labels both for supervised training and also for evaluation. And so because of these properties, and in total, in this case, we had 1,059 long-term action categories to evaluate our model on. And so because of all of these properties, so we thought that this would be a good benchmark to evaluate our model on. And so that's what we ended up doing. So here I'm presenting the results of 4 transformer variants. The first row depicts this shortest range transformer where the video inputs are only spanning 8.5 seconds. And then the last row depicts a transformer, the longest range transformer that spans roughly 100 seconds of video input. And so based on the first glance, everything looks good. So we were quite excited about this results because it clearly indicates that these long range models tend to do better at this task. But then upon second glance, we also see that the performance saturates very quickly. So in this case, just with 34-second inputs, we can already, after that, we get very marginal performance boost. And so that was quite disappointing because, well, so in this case, we're processing these 7-minute long videos, but it turns out that just by looking at the 30-second video segments, the model can already solve this task. And so for us, this kind of indicated that maybe this is not the best evaluation protocol and just in general, the benchmark and the task to do this. So after that, we kind of started transitioning into the movie understanding tasks. And movie understanding is arguably the best source of long form video data. The movies contain these really complex plots and storylines, and understanding these storylines require understanding a complex sequence of events that potentially span over, even maybe hours. And so presumably that's a good requirement for long form video modeling. But so one challenge that we ran into early while dealing with the movie data is that movies are also much longer than any existing video data. And so the computational cost of processing these movies is also quite large. So to address this computational cost, last year, we started to explore these structured state space models. And for those of you who are unfamiliar, so structured state space models, they're these fundamental models that have been out for a while, and they've been often used in older school fields like control theory and computational neuroscience. And so in a nutshell, I mean, it's just a simple recurrent model, kind of like LSTM, but much simpler than that, parameterized by these 4 matrices, A, B, C, and D, as I'm showing in the slides. And the idea is that given an input sequence U, so we'll first compute a latent sequence X, and then using that latent sequence X, we'll map it to the output sequence Y. So that's kind of the main idea behind structured state space models. And the main 2 reasons why we got interested in these models was, well, so first, as you can see from these equations, so unlike standard transformers, which have a quadratic dependence with respect to input sequence length, these structured state space models, also otherwise known as S4, so they only have a linear dependence with respect to input sequence length. So they're much more efficient and scalable, which is very attractive in considering these very long range video inputs. And the second reason was that, so as I mentioned, these models have been out for a while, but for many years, they've been struggling with even the basic tasks. And so what happened last year, there was some new theory on continuous time memorization that basically showed how to significantly improve capabilities of these S4 models. So because of this, we were quite eager to try it on video understanding tasks, especially because of the scalability of these models. And so that's what we did in our last year's ECCV paper. So we introduced this former model, basically a video transformer that also incorporates these S4 layers. And the high level idea here was that we wanted to combine the strengths of transformers for short range modeling, and then these S4 layers for long range modeling. And so the rationale was that even for long range movie understanding tasks, you still need to perceive these lower level short range cues like atomic actions, objects, and scenes. And transformers are still arguably state of the art for that. But then we also need to do this long range aggregation of all of this information with the whole info video. And so presumably these S4 layers, they might be better suited for this than any other operator out there. So that was sort of the motivation. And then how this model worked. So it's relatively straightforward. So given in this case 60 frame video inputs, as is done in VIT, we would first decompose each frame into a set of non-overlapping patches. We would feed each patch into a short range transformer encoder, so typically just a standard VIT. And then this would give us these dense short range features. And so in practice, we would get about 12,000 tokens. And so then these 12,000 tokens, we would then feed into this long range temporal S4 module to basically aggregate all of this information over the whole input video. And so I'm not going to talk too much about this long range temporal S4 module because it's just a stack of S4 layers. So in this case, it's just 4 S4 layers. What I found, one interesting detail I found about it, and it's more of an implementational detail, that unlike LSTMs or the recurrent models, in this case, these S4 layers can be implemented using convolution. So for example, here by combining some of these matrices that I talked about a couple of slides ago, we can obtain a new matrix K, and this is a very large matrix, and this can be viewed as a convolutional kernel. And so now using this matrix K, we can convolve it with our input sequence U and basically output and obtain this output sequence Y, which now incorporates all of this long range temporal information. And the reason why this is important is because just implementing as a convolution makes this entire framework more scalable and just like easier to parallelize. So this is important for training these models. And so then after we're feeding these sequences into this S4 module, after that, we can just do standard stuff like global average pooling, attaching a linear layer, and just basically predicting whatever we need to predict for these movie understanding tasks. So that's kind of the main idea. And while we're at it, I also wanted to briefly talk about the follow-up work that we're going to present in the CVPR. So this transformer model, and it's also a very similar idea, basically trying to combine the strengths of transformers and S4 layers. But in this case, the rationale for this was that for this former, what we did, so we processed the video sequentially. So we first extracted the short range features, and then we fed those features into a long range module. And in this case, we wanted to have a more flexible design that also allows us to learn these short range and long range features jointly. So what we did is we introduced this just a basic building block, which we call S4A for S4 and attention. And it also, in this basic building block, which I'm illustrating here on the right, it just basically combines S4 operation and also self-attention operation. And so in this case, this building block is pretty flexible. We can insert it anywhere in the network, in the beginning of the network, in the middle of the network, anywhere we want. So it's essentially a more flexible design. And also, as I'll show, it's also more effective than this the previous sequential architecture that we used. And so there's a lot more technical details, which I don't have time to present, but if you're interested, so check out our CVPR paper and also stop by our poster later this week. Okay, so now let's move to the evaluation. So to evaluate these two models, we use this recently introduced long-form video understanding benchmark, also otherwise known as LVU. And this benchmark consists of 3,000 movies and 30,000 movie clips from those 3,000 movies. And we primarily focus on 7 classification tasks on this benchmark. And so these tasks include things like relationship prediction, speaking style prediction, genre, writer, director prediction, and so on. And so before I go into the accuracy analysis, I wanted to also briefly talk about the computational efficiency results that we got. So as I mentioned, one of the reasons why we were interested in trying these S4-based models was the theoretical efficiency properties that it guaranteed. And so we wanted to validate that these properties hold not only in theory, but also in practice. So here we compare this former model with the standard transformer, which has exactly the same architecture as our S4-based model, but where the S4 layers are replaced with the equivalent self-attention layers. And so here you can see that for 60-frame video inputs, the standard transformer self-attention-based model requires roughly 40 gigabytes of GPU memory, whereas our S4-based model only requires 5 gigabytes. So, and we also, in the paper, we present also some results on inference time, and we also find that it's almost 3 times faster than transformer. So, which is nice because so now we kind of confirm that these theoretical properties also hold in practice. And in addition to the efficiency metrics, we also, so here we assess the accuracy of all of these approaches. And in this case, we can compare our 2 S4-based approaches with the what was at the time state-of-the-art object transformer baseline. And so here we also, you can see that basically on all of these 7 classification tasks, the S4 models outperform this object transformer baseline. So now the main question based on these results is, well, can we, based on these results, can we conclude that these models truly learn some sort of complex long-range video modeling? And maybe an even more important question, can we really conclude that this is a good benchmark to evaluate these long-range video models? And so to answer this question, I kind of try to dig into some of the experiments to try to find an answer to this question that would be empirically justified. And it turns out that it's quite difficult to do it. So here I'm presenting the results of this former model as a function of the input video duration. And so one clear trend that we're seeing here is that clearly long-range temporal context seems extremely beneficial for these models. So here you can see that going from 1 second inputs to 60-second inputs brings a huge performance boost in these models. So what does that mean? Does that necessarily mean that these models can, again, learn these sophisticated long-range modeling capabilities? And I argue that it still doesn't mean that not necessarily. And the reason for that is that we already saw like so currently our deep learning models are so brittle that even on short-range video understanding tasks, we often see that this long-range temporal context is helpful. And so this has been shown in many different works. So we first saw it in our transformer work where on kinetics, we saw that feeding 100 frames led to a huge performance boost compared to, let's say, just 32 frames. And here there's another example that I like to highlight. So this is a paper from several years ago called Long-Term Feature Banks. And so here they do validation on atomic action recognition on the AVA dataset. And it is known that fundamentally action recognition in AVA only requires 3-second inputs because that's how humans label them. But in this case, we see that the best performing model actually benefits from 60-second inputs. And so what this essentially, at least to me, what this points to is that because we have these models that are quite brittle, so even on short-range modeling tasks, they can use long-range temporal context to essentially try to resolve some spatial reasoning errors or some spatial ambiguities, but it doesn't mean that necessarily, you know, it's learning to fundamentally do some sort of sophisticated long-form video modeling. To me, this seems like just a more sophisticated mean pooling, something like that. And so if we go back to the LVU benchmark, we also observed that some of these categories, if we investigate them more closely, we see that Well, not all of them require long-range temporal understanding. So for example, this task of predicting the year when the movie was made. So clearly, even just by looking at a few frames, it's possible to do this task. Same for scene prediction. And then we also have some other tasks like director prediction, writer prediction, genre prediction, and it's not even clear. So maybe for those tasks, long-range modeling is useful, but maybe not. Maybe it's just also some low-level cues. So kind of based on my experience with a lot of these long-range video classification benchmarks, just like in my view, I don't think they're very well suited for evaluating how good these long-range video models are. And so this brings us back to the original question. So how should we evaluate these long-range video models? And so in my view, the evaluation should focus on some tasks that fundamentally require integrating long-range temporal context. So a task that if you give to a human, they can't solve it unless they leverage this entire long-range temporal context. So let me now briefly talk very briefly about some of our ongoing work to try to develop such a benchmark. And before I do that, I wanted to briefly reference some work in NLP, just because I think, in the last few years, I would say they've been a few steps ahead of us. And so just because they were working on long-range modeling for a bit longer than we did in computer vision community. And so if we look at some of these NLP models, we observe that a lot of long-range methods in NLP are evaluated on summarization tasks. And so this makes a lot of sense. So basically, given a very long document, how can we compactly summarize it? And this task makes a lot of sense because I don't think there are any shortcuts. So, just if you're given the first 10 sentences of the document, there's no way you can summarize, produce a good summary. So these models are forced to basically leverage the full long-range temporal extent to try to come up with a good summary. And so this is the direction that we've been pursuing for the last several months. And so in this case, extending this to video, so we've been working on this text-based video summarization task. So here, given a long video, roughly of 60 to 90 minutes long, the goal is to produce a text summary of that video, essentially summarizing the most important events in that video. And again, so because in this case, we don't think that there's a easy way to solve this task just by looking at a subset of a video, so we think that fundamentally it's a better task to do the evaluation. And so, as I mentioned, this is still a work in progress, but so far what we did is we manually collected about 3,500 long-range video summaries from the largest egocentric video data set, Ego4D. And the reason we chose Ego4D is because it has these long, untrimmed egocentric videos, so that last anywhere from 10 minutes to 90 minutes. So it's a really well-suited data set for this long-range evaluation. And here I'm also showing some qualitative results. So here on the left, we have our predicted summary, and on the right, we have our ground truth summary. And so even though this is still a work in progress, we see that even the initial results are not too bad. So the model is able to kind of capture some of these most important events in the video. And we also have some initial quantitative results. So here we compare our method with two very simple baselines that first extract these dense short-range captions using a state-of-the-art Lavilla model, and then just feed those captions into either a zero-shot or one-shot GPT. And then the performance is evaluated using standard summarization metrics like Rouge or BERT score. And here for our baseline, so we have a end-to-end trained baseline, which is somewhat unfair to these baselines. So we use these manually annotated labels, but we also have a much smaller model. So instead of using GPT-3, we have a much smaller decoder. So as I said, this is still a work in progress. So we need to both improve our model and also add a lot more powerful baselines for this, and just like for a more fair comparison. But just in general, right now we're quite excited about this task, and we think that maybe it's a better way to evaluate these models. And so to conclude, I mainly have two messages. So the first message is mostly related to the existing benchmarks. my experience with these benchmarks is that just because the model benefits from long-range temporal context, it doesn't mean that the temporal context is fundamentally needed to solve this task. In my view, this is more an attribution to the fact that our models are quite brittle at this point. And then the second point is that, well, I'm not going to claim that this text-based video summarization is the way to go right now. Maybe it seems like a good idea, but we'll try, we'll see what happens. And maybe there's also some loopholes that these deep learning models can find. But I think in general, I think that we need to rethink how we do evaluation on these long-term video models and come up with better and also potentially larger scale benchmarks for rigorous evaluation. And I think that that's coming up with these benchmarks will facilitate progress in this area better than coming up with new models, which we can evaluate accurately right now. So with that, I wanted to acknowledge the students in my group and all of my other collaborators. And if we have time, I'd be happy to take any questions. Thank you.
Yeah, I think we have maybe 5 minutes for questions. So if you have a question, feel free to, go ahead.
So looking at your summaries, it seems like the summaries are more focused on the generic what happened. Like there is an example of using tools, and how I would summarize that is he's building a birdhouse, right? And not that he used X, Y, Z tools, but that he built the birdhouse. So I was curious, two questions. Is that a general trend for the summaries, and how were the summaries selected? Because I've seen similar issues with like ego 40 narrations. I mean, overly generic narrations, and you can't put them together to get what's like meaningfully happening. Like
it definitely. So I think I didn't have time to discuss. There's definitely issues with the summarization task as well, and I think this is one of the issues that. I mean, there's a lot of ways to summarize these videos, and it largely depends on the instructions, like what kind of instructions you give. So in this case, our instructions were mainly, try to summarize it so that it would capture main events, like what's happening. And we also had an explicit sort of, just like, how many sentences need to be included. So I think it's definitely an issue, the subjectivity, if you ask 5 people to summarize a video, you'll get 5 very different summaries. And then, I mean, so this is also, we're still in the process of annotating. So we're still kind of rethinking what's the best way to do it. What are the instructions? Right now, also to annotate it, basically what we're doing to facilitate the process. Well, as you can imagine, I mean, like watching these hour-long videos is just very costly. So what we do, we also provide this Ego 4D captions and the snapshots of the video. So I think the summary is also somewhat biased by Ego 4D captions. And I think Ego 4D captions focus a lot on these kind of atomic events. I used the tools, I did this. So more for the annotator, maybe once they're given these captions, they think of it more of a not coming up with a completely new original summary, but I have all of these captions, which of these are important, which of these are not important.
And it's not that it's not useful, but it'd be also interesting to have that dimension of the summary.
Right.
I wonder if you could almost get the first dimension by asking GPT to summarize the Ego 40 captions.
Yeah. So I mean, we're also, I didn't talk too much about methodology, but so we have all these baselines where it's just GPT summarizing, and this is also honestly can be its own research project, just because you give GPT a new prompt and it's just doing completely different things. So so we have, I don't know how many variations of these summaries we have, and so we're exploring. I think like for GPT, especially generated summaries, I think this is a very useful also supervisory signal. You can kind of just get it for free, pretty much. So this is also one avenue that we're exploring.
Very much. I think the terms are getting so confusing for me.
Uh-huh.
So originally there was activity recognition, If you're doing something long, then that's activity, right?
Mhm.
Then there was the era of the term of holistic video understanding. I think there is even an ongoing workshop today with that term.
Right.
Then we now have long term and long form.
Uh-huh.
And I really don't see the difference between these terms. So yeah, it's just becoming a bit too much. Do you see a difference? And also, you've presented movies and Ego 4D. One is like shots, clearly, you're describing shots. And the other is like untrimmed. I also see these as completely different. I mean, your presentation gives the impression that if we solve one, we might solve the other. Is that what you think?
Wait, well, let me answer the first question, and maybe I can get a clarification on the second one. So in terms of, I think, yeah, I think this confusion, I think you're not the only one. I think in general, a lot of us are confused, and I think that also relates to this maybe lack of existence of good benchmarks, because some people think, well, yeah, if you have like 100-second video input, that's necessarily long form video modeling. But maybe, you know, you don't really need 100 seconds to do it. Maybe it's just like, I mean, even like for, as I said, like for data sets like AVA, which is, it's short-term recognition, but you can still get 100-second video inputs. It doesn't make it long-form video modeling. So I think, yeah, for me, like the confusion is sort of the input side versus the task side. I mean, does the task really require long-term video modeling? And I guess like what I was trying to make a point at this talk is that I would say that at this point, we don't really know what the good tasks are for long form video evaluation, because a lot of these, like we're used to doing activity classification, like activity recognition, video classification, because that's what's happening in short-term modeling. But I don't think that it works the same way. And so I think, yeah, it has to be something fundamentally different.
Building the bird nest. This is like video classification.
Right. So this is also the first benchmark that I presented on how to 100 million. That's exactly what these labels are. But then you do see that there's this issue that, well, I mean, yeah, the model can just look maybe at the last few frames, and it doesn't need to know anything beforehand. It just knows, well, this is the activity. So is that really long form video modeling? I would say that not, but yeah. But I think the point is that I don't have these answers, and I think that's I would like the community to kind of try to think more about this and come up with sort of, okay, this is a task that makes sense for long form video understanding. This is a benchmark that makes sense, not just because, oh, yeah, here we have 100-second video inputs, that's automatically long form video modeling. Yeah. So what, sorry, I don't know, I don't want to take too much time. So what? No, yeah, I don't think it's the same. I think, yeah, for movies, so what we did, and I didn't have too much time to talk about it, but we explicitly, I don't know, and maybe this is also would work for Ego 4D, but yeah, for movies, we explicitly rely on the shot detection, and we do analysis, like, yeah, like we process shots and then we try to aggregate the shots, but I mean, in egocentric, you don't have this, like, I mean, it's just like uninterrupted camera feed, so it's very different. So yeah, I don't think that, I would say the two are kind of quite different. Yeah.
Maybe just one more question.
Yeah, I just want to ask, like, so in the ALB domain, right, when people like read the text, we kind of need to, like, when we test by the person understand the text, we ask them question, like, you know, question answer. Do you see like in like video question answering could be like a better approach compared to video summarization, because it might be like, you know, less subjective? Also, I think a video question might be there's some actions that are let's realize more context. Let's say it's suicide, right? Some suicide maybe not very obvious. You need to contact like whether you take a pill or you're sleeping or you're kind of suicide. So you kind of longer contact. Do you say like basically like just two alternatives? Do you have any comments say whether it could be like a better benchmark?
I mean, yeah, I think question answering can be, I mean, right now the question answering that we have is also kind of, it's everything's done on just like these trimmed video clips. So I guess I would sort of see it as if you have a very long video and then, I don't know, like even in these egocentric videos, like somebody just asks a random question about the video, I guess like it's it's more, I view it as a localization problem. It's hard to say. Like for me, I would basically given a long video and a question about like one of the segments of a long video, like you can probably solve it just, first localizing where the question is happening and then using some short range model to answer that question. So I don't know. I mean, we're definitely thinking about this also, if it's possible to kind of, given that we're in this NLP domain, whether we can extend also from summarization to QA. And yeah, I'm still, I don't have a good answer for that. Like to me, I don't know if to me, it seems like more like a temporal action detection problem, almost like that, except that instead of localizing an action, in this case, you're localizing the question. Where is this question appearing in the video? Yeah.
It depends on how you frame the question, right?
Yeah.
The question like really asking a short clip, I think.
Yeah, but so I guess like the bottom line is that I think, there's a lot of questions to kind of, as Dimo was saying, about definitions of the benchmarks and what constitutes long-term modeling and what does not. Okay, yeah, thank you. Thank you.
Hey, Keith, could you hear us? Or?
Hey, Mike. Yes, loud and clear. Loud and clear.
Cool. Yeah. Yeah, I'm trying to actually, maybe let me just
Can you see my slides?
yeah, perfect. Cool.
Am I good? Well on?
Cool. Yeah, let me maybe do a quick introduction of you first, and then you can start your presentation. Yeah, so Kees Nok is a full professor in computer science at the University of Amsterdam, where he has the vision and image sense lab. He frequently serves as chair of many major conferences in computer vision and multimedia, and also an associate editor for computer vision and image understanding, palming, and he has a lot of work on multimodal video models, action recognition, localization, and so yeah, today he will be basically talking us about how to break in the spatial video bias and how this can help to the norm for. Yeah, so let's welcome Kees.
Well, thank you for having me, and sorry I couldn't join you in Vancouver this week. I very much like the topic of this workshop, long form video understanding. That is the holy grail that we need to achieve. I cannot contribute much to long form video understanding yet, but we looked at the shortest form of video understanding. That is simply glorified image classifier. And that is basically the spatial video bias I want to talk about today, and how we can break this spatial video bias. But let us first look at what we achieved. So it is always good to copy back some old slides from old talks from yourself or from other people. This is from Dutran while at Facebook. And yeah, this seems so simple to classify what sport you see in a video, but it is quite amazing, especially for people who have been in the field for longer. It is really marvelous progress, and this seems decades ago. But it's not that long ago, actually. Here's another example, prompting a video to identify what pixels belong to the gray dog running on a leash during a dog show. And so this is what we can do in video understanding. Here's another example from ICV last year. This is video relation detection, so detecting the object and another object and their relationship. So an adult cleaning a horse here, for example, and then trying to maintain the boxes as both objects move throughout the video. And yet another example.
I've got everything I need. I figured life's a gift.
So trying to detect not only what action is happening, but also the spatio-temporal extent. And this is actually quite amazing that we have all achieved this, and even better stuff that is happening this week at CVPR. Yet there is a problem, right? So there is this phenomenon of a spatial bias in video understanding, and many people have looked into this problem. So we are certainly not the first to raise the question of whether video models truly understand time. So prior work has already shown that existing video benchmarks do not sufficiently test for temporal understanding, and one can get indeed quite far with a single image or a time invariant pooling of video frames. So in this talk, I would like to talk about breaking this spatial bias, and I will highlight two recent works from my team in Amsterdam. And the first one considers breaking the spatial bias in video contrastive learning. And the other one considers breaking spatial bias in video language foundation models. So the first one is joint work with Vida Toker and Hazel Doughty from Amsterdam. The work is called Tublet Contrastive Cell Supervision for Video Efficient Generalization. You can find it on arXiv. So let me briefly recap what is video contrastive learning. So we have unlabeled video data, and we learn a network based on some proxy task where we have small transformations of one and the same video, and we force those to be similar. And by doing so, we can train a network in a unsupervised fashion. Now, once we have optimized the weights, we can use this network for a smaller set of labeled video and fine-tune it for a task at hand. For example, action classification on UCF 101 or HMDB 51. Now, in this contrastive learning, there is a huge spatial bias. So as you can see on the two golf videos on the left, although they are not identical, so they have been transformed a bit by cropping and jittering, but still the algorithm can learn shortcuts, right? So it's still the grass that is the key differentiator, and the same for the skiing videos on the right. So although the videos are not identical, the shortcut is easily learned. So video contrastive learning still favors coarse-grained features. And this limits generalizability, so it is unsuited for fine-grained video understanding. And also the motion variety constraints in the data cause data hunger. So what I mean to say here is that as the variety of motion patterns in existing data sets may be limited, your algorithm will need much more data to see actually all these kind of subtle motion variations to learn a reliable model. So it becomes very data hungry. And this is, of course, to be avoided. Now, we have a very simple proposal that works really well. So the key idea is to add two videos, synthetic tuplets during pre-training. So what we do here is we take two different videos, and in each of those videos, we sort of paste an identical tuplet of a patch that moves through space and time. And this patch is identical in both videos. So in terms of pixels, it's identical. And by doing so, we force the contrastive learning to learn the similarity between those tuplets and also between negative tuplets. And this is a very powerful mechanism. So let me explain to you how we get to these tuplets. So we have two different videos, and from one of those two videos, we take a random patch. And from this patch, we simply paste it onto subsequent frames of each video, and this generates a tuplet. But this is a rather boring tuplet because it does not contain much motion. So in the second step, we add motion to each patch, so that we can learn motion-focused video representations. Now, we have considered linear motion and non-linear motion. So in the linear case, the patch follows a linear trajectory, for example, by sampling a patch on locations for 3 keyframes and then linearly interpolating between locations. Or we follow a non-linear motion pattern, and then we simply sample a set of 2D coordinates from uniform distributions, and we apply Gaussian filtering to smooth the trajectory. And here you see some example of tuplets that we can then generate. So this is pure synthetic. We don't need any huge data sets to create those. The tuplet motions are simulated by changing the position of the patch across the frames in a video clip, typically with translation. But in reality, the motion of objects in space may appear as other transformations in video. For example, scale decreasing as the object moves away from the camera, or motions due to planar rotations. So motivated by this, we propose to add more complexity and variety to the simulated motions by also transforming the tuplets. And here we consider 3 variations. So we scale the patch across time, or we rotate the patch, also using in-plane rotations, and we also apply shear. And now with these set of tuplet transformations and the motions, we are able to simulate a rich variety of subtle motions in videos. Now, then comes the final step in our approach. So what we do is we overlay 2 identical tuplets into 2 different videos, and this forms a positive tuplet pair of 2 videos. Then we learn similarities between clips with the same tuplets, the positive pairs, and also clips with dissimilarities between clips with different tuplets, the negatives. And here we simply use a contrastive info NC loss. And this works really, really well. So here are a bunch of ablations where we evaluate on subsets of UCF, fine Jim, something, and also a fine Jim subset. And the baseline is basic video contrastive learning. And then we show here the effect of tuplet generation, tuplet motion, and tuplet transformation. And as you can see, really the tuplet motion and transformation give a big jump in accuracy across all 4 data sets. We also consider the types of motion, and not completely surprising, but the nonlinear motion was the most effective. We considered the different transformations, also their combinations, but we found that only rotation is basically good enough. And then we also varied the number of tuplets that you can extract per clip, so you don't have to paste only 1 tuplet into 2 videos. You can also do multiples, and we found that two tuplets gives a good trade-off. And what does this model then learn? It's actually quite interesting. So on the left, you see a class-agnostic activation map without fine-tuning on fine Jim using video contrastive learning. So the default contrastive learning with spatial bias. And as you can see, it has learned shortcuts, predominantly in the background. Whereas our proposal really learns to attend on the foreground motion, so to say, on what moves, without ever having seen any fine Jim videos during training. So that is quite interesting. This is all only trained on Kinetics 400. And then it has another benefit. So here we compared our tuplet contrastive learning with normal video contrastive learning and learning from scratch. And as you can see, is beside the fact that we're always better than the 2 alternatives, we are pretty stable also with only 25% of the pre-training data. So with 25% of Kinetics 400, we still beat most of the other approaches. And this is because we basically inject lots of fine-grained motions in Kinetics 400. And by doing so, we need less data during training. Well, how does this compare to state-of-the-art? So we took a R2+1D backbone and pre-trained this on Kinetics 400, and we compared with a bunch of methods. And our approach performs well, also compared to methods using RGB and audio or RGB and flow, where we only need RGB. And interestingly, when we train our approach on mini kinetics, which is 3 times smaller than Kinetics 400, we still outperform all the existing methods using this backbone. And in the paper, we also tried an S3D backbone, and it has the same conclusion. So that's actually quite interesting. Then we also compared on the CVPR benchmark. So this is some self-promotion. This is a paper from Vida Toker that appeared at ECCV, where we propose a benchmark that considers evaluation beyond UCF and HMDB, as it's so similar to Kinetics 400. So basically see how it will generalize across domains, samples, actions, and tasks. And also on this benchmark, we beat all the existing methods. And again, when training on the 3 times smaller mini kinetics, we are still very, very competitive. So a few key takeaways on tuplet contrastive learning. It is a simple and effective self-supervised video representation learning that breaks the spatial bias. It is very data efficient. You can do pre-training with less unlabeled video data and still get good results. And you even get better generalization for free, because it really focuses on fine-grained motion data. And this is key for generalization. So that is the first topic I wanted to talk about. And the next one is breaking spatial bias in video language models. And this is a work that is done together with Piyush Bhagat, master student from Amsterdam, and Makarand Tapashwi from IIT Hyderabad. And this paper appears at CVPR this week under the title Test of Time, Instilling Video Language Models with a Sense of Time. So here, the problem is foundation models are great. So they provide the language interface together with a few or no training examples to do marvelous things. And yeah, this has enabled downstream adaptation on a variety of tasks using a language interface and with only a few data samples. So this is great. So you ask here, what does this picture show? Together with a picture of a dog, and the language model will come back to you and say a dog running. Now, for video, this is particularly attractive because we don't want to annotate every single frame all the time. And basically, these models can do the same thing. So what does this video show? And it will come back with an answer like a kid eating ice cream. However, despite the massive scale of pre-training datasets, we challenge if video foundation models truly understand video beyond what can be understood from static images. So do these models really understand video, or are they still glorified image classifiers, so to say? So we ask, do video foundation models truly understand time? And our idea is to come up with a test of time where we ask the video language foundation model questions that have temporal relationships. So rather than, so here we, for example, ask, the baby eats ice cream before walking downhill, true or false? And then we expect the model to answer with false. Now, we created this test of time, which is essentially a small-scale synthetic benchmark that measures whether these video language foundation models have spatial image bias. So what we did is we created very We consider videos that contain two events, such as a red circle appears and a yellow circle appears. Then we get a caption for this video by stitching the text with a temporal relationship, in this case, before. So a red circle appears before a yellow circle video. And this we consider a positive caption. In the same way, we can obtain a negative caption by simply swapping the two text segments around the temporal relationship. Now, the test for the model is to select which of these two sentences is consistent with the time order of the video. So it should say that this is the correct one and this is the wrong one. To verify whether the models can still perform reasonably well also on this type of data, we also create a control task where we only provide a single event and a simple caption. For example, a red circle appears. And it has to say that this is indeed the red circle and the yellow circle is the negative caption, so to say. Now, what did we find? We considered 7 openly available modern video language models, and we had them execute this simple test of time task as well as the control task. And this is what we found. So they could all do the control task very well, up to 100%, but none of them was able to do the time order task. So they are all at chance or below chance even. Now we have a problem because, yeah, we are academics and we have an academic compute budget. So we don't want to train our own video language foundation model from scratch. So what can we do to break this spatial video bias without training from scratch? Now, luckily there is hope. So we use a technique is called post pre-training. So instead of training from scratch, we run another round of pre-training with a much smaller set of annotated videos. So how can we go about in this post pre-training setup? So we take as input data any dense video captioning dataset that has multiple events in a video. So from a single video, we take any 2 non-overlapping clips. And then what we do, we stitch them in time and we stitch the caption accordingly with a before or after relationship. So here you see example, the yellow segment appears before the blue segment, or the bottom one, the yellow, appears after the blue one. And by doing so, you can create temporally aware video language data sets that are very beneficial for this post pre-training procedure. Note that for this example, we can also construct negative samples easily, and even more so. So here you see again how you create a positive sample as well as 2 negative samples. Now we have a base model, and here our investigations focus on video clip. It uses S3D features that we feed into a BERT video encoder. Then we do mean pooling to obtain our video representation, and the sentence together with the class token we feed into a text BERT encoder, gives us a sentence representation, and then we are ready to do our real post pre-training using again contrastive learning. So we start with the usual contrastive learning setup, where for a video, the corresponding sentence serves as a positive, and all other sentences in the batch serve as negatives. Then we apply the time order reversal to the sentence, which swaps the order of events in the text. These serve as additional negative sentences. 1 for reverse sentence corresponding to the video, and 2 reverse sentences for other sentences in the batch. Likewise, we apply the same function to the video to construct its time order reversed version. So this gives us even more negative and also positive videos, so positive pairs that we can use for post pre training. We apply a standard contrastive loss, and we use different hyperparameters to control the impact of each of these parts of the similarity matrix. And we term this recipe as TACT, temporal adaptation by consistent time ordering. And as a baseline, we also consider only applying the usual contrastive loss on the top left quarter of the matrix only, which we call the non-temporal baseline. We did experiments on a bunch of data sets, so tempo, ActivityNet, Cherate's ego, and we create artificially stitched clips as described earlier, and we perform some experiments. So here we consider two tasks, text to video retrieval and our test of time. So for retrieval, we look at usual metrics such as recall at 1. And for test of time, we look at temporal accuracy, which is the fraction of test samples where the model correctly associates a video with its time order consistent sentence. Now, in comparison to the baseline, on all data sets, we observe that the retrieval performance is either maintained or improved. But more importantly, the temporal accuracy significantly improves with our TACT adaptation. So the blue area is the sweet spot where you want to be. And the more you are in this top right corner, the better. Performance varies among datasets. So on tempo, we get a good boost. On Cherate, the improvement is much more modest, but in general, the trend is the same for all the 4 datasets. So we can basically instill some notion of time in an existing video language model, which I think is quite appealing. We also tried whether now we could solve our initial task we started with, our test of time. So if we do post pre-training of video clip with tempo, the accuracy on this time order task goes up from chance till 64.4. For ActivityNet, the gain is more modest, but for Cherate and Cherate's ego, we get very good boost also. So TACT is much better than random. That is the conclusion here. So far, we only considered before and after relationships in our post pre-training. So we also evaluated whether it could generalize to other prompts. And to probe this, we additionally run an evaluation of TACT adapted models on sentences such as first event 1 happens and then event 2 happens. And on this new unseen prompt 2, TACT again does much better than chance, which indicates that TACT is indeed learning time order of events across video and language. So we are happy with those results. And furthermore, we ask if models adapted with our narrow definition of sense of time, narrow because we only consider before and after relationships, can benefit more general temporal reasoning tasks. To answer this, we take TACT models and evaluate them on the following tasks in a zero-shot manner. First, we consider temporal benchmarks, such as something and the temporal subset of kinetics. On these, we run the action to video retrieval task, given text description of an action, and we want to retrieve the most relevant video. Second, we consider temporal question answering, where the questions have a temporal aspect, such as before, after, during, and while. We find that TACT adapted models show promising benefits over non-temporal baselines on all these tasks. So sometimes the gain is small, but sometimes, for example, on this question answering benchmark, the results are quite impressive. So that brings me to the key takeaways on video language models. So we propose a test of time for video language models. Existing models fail this test, much to our surprise, actually. Our simple TACT recipe instills a sense of time without the need to retrain these huge models from scratch, but instead uses an efficient post pre-training procedure. The adapted models show promise beyond the temporal relationships on which they have been post-pre-trained, and they even generalize to more general temporal reasoning tasks. We think this might also be interesting beyond instilling time in video, so maybe also other properties can be instilled in these video language models. That brings me to the overall conclusion of this talk, and that it's about time to break spatial video bias. We have shown 2 examples how this can be achieved, and I think there is much more left to explore. And with that, I would like to end my talk and open the floor for questions, should you have them. Thank you.
Yes, thank you, Case. Actually, we have a couple more minutes for questions. I guess if your question can just come over to the front and yeah, maybe try that one first. We see. I guess not. Yeah, maybe.
Can you hear me? I don't know if you can hear.
Yeah, I can hear you.
Oh, good. Okay. So what I'm wondering is, you've been working on this problem for a while, you've done the various tubelets things. What's your intuition about, like, what do these models really know about video? I mean, like, I think like deep learning has struggled with video for a long time. Like, what do you think it knows, and what are some amusing things you think it actually doesn't know yet?
Yeah, so I think that many of the models that we have that claim to do video are basically just image classifiers on steroids. So they have very limited temporal understanding, and I think, but there's still a lot to gain, especially if you use multimodal approaches. So including sound, and also this language provides a much richer sensory experience that allows us to learn much better models for video. So I'm not sure whether that answers your question.
Yeah, looks like it solves his questions. Do we have more? Oh, actually, I think there may be one come from the chat channel.
Hi.
So
Can I ask the same question for video?
sure. Yeah, maybe go ahead.
Thank you for presenting the work on, just checking whether the vision language models are actually checking the time. I went through this paper like a few weeks back, and I was lucky to have you over Zoom. The question I have is, how did this pre-training work? Like, how did you manage to not end up like, leading into diminishing performances from actually pre-trained data, which is trained on a larger data set? That's the question. And can you also elaborate like how you could, you're just, making a data set by I couldn't understand like how you could create a new data set just by changing the before and after of the time. Because if you look into deeper, say if you're looking at an action, right? Action has a lot of steps. And it can go by A, B, C, D, and it continues like that. There's logic involved. And how did you create such data sets like that in the fly?
Well, so to first answer your first question, so this post pre-training procedure is quite evolved and is very sensitive. So it is not a general recipe that will work for all video language models that you can then instill this sense of time. So Piyush did try it on several models, but on many of them it didn't work. So on video clip in particular, we got very good results. But so it is not a general procedure that will work for any method. I think the point that we want to make is that it is feasible to instill this notion of time in existing video language models with a rather lightweight procedure. And I think much more research is needed to investigate what other lightweight procedures can be explored to inject properties into these models that we want, so to say. So that is one. And then the second is, yeah, you're absolutely right. We did very simple before and after relationships. And if you want to have like this vision of long form video understanding, we need much more complex relationships and logic and reasoning abilities. I fully agree. We focused on something simple to make it easy to measure and to also easy to create the data that we needed for post pre-training. So we took existing video data sets like tempo, where you have multiple events in the video, and we simply stitched those together to create sort of new videos, right, and new captions. So we use the existing data set, but we adapted them a little bit by using these before and after, explicit before and after relationships. So to really force the model to learn what we wanted to learn.
But did you also run experiments on charades, which is already a long form video data set, which
yeah.
has a series of actions?
Yeah, I think.
And how did you create?
I don't know it by heart. So I can look.
I mean, I can also look at the paper. That's not an issue, but I just wanted to hear from someone who has really done, like, has experience doing this.
Yeah, if you want to have the real answer, you have to ask Piyush, because he did all the experiments.
Thank you so much, Professor.
Yes, thank you. I guess we can maybe take just one more questions then. Yeah.
Hi. So I was wondering about something you just said about the path forward for action understanding, and that you said language was a good thing. I forget exactly what you said, but you said that it helped model like more complex, types of actions. And I'm kind of also wondering, is there maybe some hesitation on your end in that language just is much more inherently complex than action? Action is really very simple when it comes to at least like base physical action, and language doesn't really allow for the separation between the different types of contexts. Like, you think of like a monkey moving food to its mouth, a monkey eating food, a monkey taunting another monkey. Those are all like the same actions described in language, but are extremely different. Do you think maybe we should solve a problem that's very simple first, when it comes to like base movements, and then move our way up towards, doing the hard things,
Yeah, so what is simple and what is hard? That is, we don't really know, and often the problems that seem very simple end up to be very hard, and the hard ones actually are very simple. So I think with language and combination with video, you can have much finer grained descriptions of what is going on. So, for example, together with Hazel Doughty, I looked into adverbs to consider whether an action is executed slowly or clumsy or right. So
yeah,
it gives very precise description, and how to recognize those is actually quite challenging.
Yeah, I also think like it's very hard to describe an action. There's a lot lost when it comes, like, when you introduce language. Yeah, I agree though. Yeah, I totally get what you're saying. That makes sense. But I do think there is a simplicity to action, like when like how many physical movements can you possibly, like, I'm sure there's like some, like, people have thought about like taxonomies for physical actions, like, we have a paper on Thwerblig's, 19th century creation of physical movements. So, like how you can reach, grasp, move, use, etc. Like,
Sure, but you can combine this with any noun. So I mean, as humans, we first learn nouns and then we learn verbs, because the set of nouns is much more restrictive than the set of verbs and nouns, right? So that gives you
Right.
an endless repertoire of things you can act upon.
Right. Yeah. The nouns are the infinite part of this, but yeah, I agree. Okay. Thank you.
You're welcome. You're welcome. Like the question.
All right, let's thank the speaker again.
Thank you so much
Yeah, thank you.
for your time at
See you.
CVPR. Bye-bye.
Yeah. See you. All right, so I guess the next part is to kind of like briefly go over the challenges we host at this workshop. So Difei, do you want to maybe? Yeah, so I think just as Gadas mentioned, that one of the purpose for this workshop was to brainstorm and come up with the benchmarks that would be really look into the issues and tasks we want to do with the long form video understanding. And so that's why we come up with these a few benchmarks. And the good thing is that I guess that the performance on these benchmarks are really pretty high, 90, especially for the, I guess, first track is already 90 something. So almost the solve maybe. And looking forward, maybe we are trying to come up with new tasks, and feel free to let us know if you have some good ideas. Maybe you,
Okay.
yeah.
Thank you, Mark. Then I think I will go over our challenge this year, and 2 minutes. Okay, let's start it. First, I think with the recent advancements in large-scale language model and visual foundation models, we have paved the way for the development of the truly effective multimodal AI assistant. I think also, Also, I think long-form video understanding is quite very important for building a multimodal AI assistant. I think why is it? Because in many real application scenarios, the inputs or the outputs are long videos. For example, this is a video about how to use in the GoPro, and maybe you want to know in my case what is the setting about, and actually you want the AI can help you by breaking down each step from a very long video and answer your questions and even guessing what the comes next. And similar to the video understanding, for the video editing, users also provide some long videos to the AI to be edited. So to wrap up, understanding and making long videos will help the AI assistant to be more helpful and creative. So now a question will naturally rest: how can we solve it? How can we learn modeling the long form videos? Actually, some cognitive science have revealed a very simple phenomenon that when humans watch long videos, they naturally divide the content into several chunks. Actually, this type of segmentation happens intuitively without any needs of predefined class or some explicit instruction to do so. So one important step towards the long form understanding, we think, is learning how to break down a long video into several chunks. So here comes the first track. It is hosted at the first year of our lab workshop. It's called generic event boundary detection. I think the main goal of this benchmark or this track is let the model to localize moments where humans naturally perceive the event boundaries. For example, a simple boundary could be a shortcut of a long video, or a boundary indicates the change of the subject from the run to jump. Actually, there is an open vocabulary boundary we need the model to perceive. So correspondingly, more formally, we propose the first track, generic event boundary detection. So given a video, we want the model to output the timestamps of all the boundaries within it. And also we propose a new evaluation protocol. It's called the relative distance. And this is compare the prediction and the ground truth timestamp. And usually a video will contain several timestamp of different boundaries. So we further calculate the FE score to calculate the final score of one video. But actually, only understand where is the boundary of a video is not far enough. So we also want the model to know why it is a boundary. I think the model needs to know what has happened in this video, in this video, what is the subject of the events, and what happens before and after at the moment of the event boundaries. So I think we think it is also a crucial step towards the multimodal understanding of the long videos. So here comes the second track, generic event boundary caption. So in this task, we want the model to given a video and generate given a video and the ground truth boundaries within it. We want the model to explain why it is a boundary. Specifically, the model needs to output 3 types of caption. The first caption is to depict the subject, and the other 2 is depict what happens of the subject before and after the boundary. And actually, we just use a quite commonly used evaluation metric like SPICE, range, and setter to evaluate the similarity between the prediction sentences and the ground truth sentences. But also, as last year, we found actually either the GB generic event boundary detection and captioning is all about diagonal benchmarks. We mainly use them to probe the model if have some basic abilities. It is still far away from some specific application scenarios. So this time we want to propose a benchmark that can fully mimic the scenarios of how AI assistant help users. For example, we want the model to guiding users while operating some complex devices like a washing machine or GoPro or a complex Microsoft, something like that. So here, the more specific our task, the setting is like that. Given instructional video with proper script, and also we also provide some visual query and textual query depict what issues the users are currently encountering. So given these 3 types of input, the model is required to answer a sequence of multimodal questions, multi-choice questions. So actually, this type of multi-step affordance-centric question-driven task completion is quite similar to another challenge, another task like multi-round visual dialogue. So we inspired by these metrics. We also use the retrieval-based metrics to evaluate the tested methods. So specifically, there are some recall at K and mean rank and mean reciprocal rank to evaluate the models. So all previous 3 tracks actually are proposed in previous 2 years. And actually, what is new this year? This year, we propose a guest track called cross-modal video retrieval dataset with reading comprehension. So what makes different between previous tracks? Actually, in the previous tracks, we mainly focus on the visual appearance or actions in the video. But actually, there are also a lot of information in videos comes from the text in frames. For example, we are watching a live stream of sports. Actually, there are a lot of text during the different frames. The text will show actually the current progress of the video, the player's name or the scores, etc. So actually, we want the model to also comprehensively understand the text and visual appearance in a long video simultaneously. So actually, let's summarize the features of this new proposed data set. We call it text VR. So the captions include semantic information from both text, OCR tokens, and visual contents. And also, we propose a very high resolution video data sets. we want to capturing more fine-grained text and OCR feature. And also compared to previous benchmarks, text we are considered more on text. For example, for the videos part, actually 82% of videos on TextVR contain at least 20 text instance. It's much more than the previous data sets. And also for the query side, I think the most queries on the TextVQ data set contain at least one text OCR token. Actually, while the queries of previous data sets like MSRVTT or Yokuku2 almost don't contain the text or OCR token in their query side. So basically, this new track is formulated as given a video and OCR related sentence query. The models are expected to retrieve and return the relevant videos. And also, this benchmark is borrowed from the traditional retrieval datasets. We use recall at K and min rank, and also the median rank to evaluate the tested methods. So I think there is also a very difference between the previous year is actually we has studied about the reverse version of the understanding problem. Actually, we can also see there are rapid development of stable diffusion models on the video generation or image generation. But I think most of the work are still focused on the image or short clips. So this year we added this new track. And more details of this track will be illustrated by our lead of the track 4, Forest, and he will introduce more about the detail of this section. So I think next step we will announce the winner of this track of today of the tracks in this year.
They cannot see the screen. Maybe we need to share.
Oh,
Sorry.
I think it's not okay.
Okay. Yeah, just keep everyone.
Yeah. Okay, I think first I would like to thank all the participants come from the different places of the world and from both very excellent universities and some very excellent companies, including Tsinghua University, Tencent, Huawei, etc. I will very thank all the participants for the attending of these competitions. So first, I think I will briefly recap the leaderboards of different tracks. First is the track 1, generic event boundary detection. So this year, the winner of this year achieves a very high performance, 0.86 FE score. Actually, is quite a promising results. So I think they propose a very efficient methods to overcome this type of challenges. And also for track 2, the generic event boundary captioning. Compared to the last year's winner, the winner this year improves the performance from the 0.74 to 0.76. And also for track 3, actually the winner of this year achieves a very huge performance boost from the 0.45 to 0.79. I think it is quite intriguing to see this kind of results. And also for the newly launched guest track, the winner method significantly outperform our proposed baseline. So first, I think I will announce the winner of the track 1 to track 3 and the guest track. So first, I will graduate the team camp from the Tencent companies and Tsinghua University, which wins the first place award of the track 1 generic event boundary detection challenge. And also, we will congratulate the team PRL from the Chonam National University, which wins the second place award of the track 1. And also the team from the team's SUS Tech VIP Lab from the Southern University of Science and Technology wins the first place award of the Track 2 Generic Event Boundary Captioning and Challenge. And for the team, Tom Chen CTG from the Hunan University and the University of Central Florida wins the challenge first place award of the challenge of the Track 3. And also the team BDAA Mine from the University of Science and Technology of China wins the second place of the Track 3. And also I think the winner announcement for the Track 4 will be presented by our Track 4 leader, Forrest. So I think I will skip this time. And also for the guest track, congratulations for the Intelligent Perception and Image Understanding Lab from the Xidian University, which wins the first place award of the guest track. And also the guys from the same lab but different members, also from the Xidian University, won the second place award of the guest track. I think congratulations for all the participants and all the winner teams, and appreciate your efforts on designing such very wonderful methods. So I think that is all of my presentation of the overview of the challenge and the winner announcement. So I think maybe we will get a coffee break, and yeah, and after that we will invite the winner to present their methods, and also there are some talk about from the Forest to present the Track 4 video editing works. So thank you.
哦，他们都要开 live 视频还是不要开？那个是80。我哦，没有，我是在哦，可以知道一下，也不是就是从过关身份检查，我这里是。
Hello, Yuanxi. Maybe you can test if you can share the screen.
Okay.
I'll sit there. Okay, sure. Thank
Yes.
you.
Okay, let's see. Okay, can you
Yeah.
see my screen right now?
Yeah, I
Okay.
see. Yeah. Okay. Sounds
So
great.
should I start right now or wait for 5 minutes?
Maybe it's wait another 5 minutes. I will start at
Okay.
10. Thank you. Thank you.
Okay.
Hello everyone. Welcome back. And I think first I will invite the first place award of the track one, the excellent team from the Tencent Holding and Tsinghua University to present their winner methods on the track one. And let's welcome the track one winner. Can you start, Yuanxi?
Okay. Hi everyone. So we are the team Camp and we come from Tencent Interactive Entertainment Group, Common Data Platform Department. First of all, let me express deep gratitude towards the organizers who held this generic event boundary detection workshop. And it is an honor to represent our team and present our method here. So let's get started. Wait, just wait a minute. Can I go to the next page? Let me restart it. Okay. For this task, we cut the video into equal length short sections as shown in the graph. The segment was treated as positive if there was a boundary there and negative otherwise. However, the proportion between the positive and negative samples is highly unbalanced. The boundaries are classified as multiple classes, including short changes like cut, slow, and fast motions, event changes like action, subject changes, and object interaction, gradual changes like fading, dissolving, and zooming. However, the definition of the generic event boundaries is very subjective. Each video in Kinetic GEBD has 5 different manual annotations from different persons with huge differences, and the location of the boundary might not be labeled very precise as well. Our model structure is largely based on our method and framework used last year. We applied MAE in our models dealing with the GEBD task in 2 stages. In the pre-training stage, we split videos into patches and maxed out 90% of the training data. We used a pixel-wise reconstruction loss to pre-train our model and get the video embedding and encoder. In the fine-tuning stage, we designed 2 headers using the BCE loss and MSE loss respectively to predict the boundary location, and the results from both are get averaged to get the MAE output. Besides the MAE pass, we also use contrastive learning with temporal self-similarity module as well as a direct convolution layer path to also make predictions on the boundaries. All the outputs from these 3 different paths are then get weighted average to get our final prediction. In our last year's project, we used a pseudo-label strategy in training all models. We want to take full use of the unlabeled data in the data set. Therefore, after the model gets trained for a while, we use the model to make predictions on the test set and then use the pseudo-label data to train the model again. In our new project, we also extract features of extra non-kinetic GEBD videos and acquire their pseudolabels. We explored the effectiveness of this strategy in relation to the amount of pseudolabels we used during training. The experiments results are shown in the table. As we can see, using more pseudolabels of the GEBD test set generally yields more improvements on F1 score on the validation set, while using pseudolabels of non-GEBD data is generally harmful to model performance. That's probably because the distribution of the non-GEBD dataset is different from the GEBD test set. According to the experimental result, we finally trained all final models by using only pseudolabels of the 18K GEBD test set. We also consider that the difficulty of the GEBD test is highly correlated with the number of boundaries of each video. More boundaries means that the content of this video is more complex and it is more difficult to detect where the boundaries are located. For this reason, on BCE loss, we apply the focal loss strategy. We assign higher loss weights to videos with more boundaries in the annotation, and the loss is computed as follows, where S is the number of training samples, Ni is the number of boundaries in the ith video. Therefore, more boundaries in the video will give it a higher weight during training, and the videos with more than 10 boundaries may even get a weight higher than 1. By using this focal loss strategy, our model gained a 0.05% improvement on the F1 score. According to the distribution of this data set, we developed a post-processing strategy called segmentation alignment in last year's competition. To put it simply, since manual annotations will not appear within the 0.3 second of the beginning and end of the video, and a predicted boundary is regarded as a true positive if it falls into a plus or minus 5% of the video duration interval around the boundary. Our strategy will then shift according to these conditions to make the true positive covers a larger range. You may refer to our paper last year for more detail. In order to improve this strategy further, first of all, we explored the distribution of the data and roughly classify all the data into the following groups in this table. First of all videos are divided into 4 categories according to their duration, including 0 to 4 seconds, 4 to 8 seconds, 8 to 10 seconds, and about 10 seconds. For the first 3 duration categories, the videos can be then divided into 4 types: no splits, 0 to 0.55 splits per second, 0.55 to 1 split per second, and more than 1 segment per second. For videos of about 10 seconds, due to the large volume, we divide them according to the number of splits from 0 to 9 and 10 plus times instead of using per second. Using the old version of the segmentation alignment strategy, there are 10.61% of the video get a higher F1 score, and only 2.75% of the video gets a lower score. We can get more information by looking into each group. Here are the top 5 most promoted group, and we can see that this strategy has a greater impact on videos with more annotations. This is because only when the number of annotations is sufficient will it be affected by our restriction, and a chain push will occur. However, we can also see that this group with 10-second and 10+ splits has a relatively high reduction ratio. This may be because our push strategy will directly discard some splits to meet our spacing requirements for some overcrowded videos. This overly aggressive strategy may hurt some correct answers and result in overcorrection. Therefore, we consider this group 10-second with 10+ splits as a possible improvement direction. In the new strategy, we tested the most suitable intervals between 2 adjacent boundaries for the above 23 groups of videos and make changes respectively. After this adjustment, our target group has a lower reduction ratio as shown in the table, which met our expectation. The results show that the new strategy can improve the F1 score by about 0.03%, and just making changes on this 576 videos in the target group only can make an improvement of 0.023% already. Applying this new strategy to the test set, we get an improvement of 0.04% on the test F1 score as well. Finally, we trained 3 kind of models using different structures: MAE-based models, contrastive learning models, and direct predict models. For contrastive learning models and direct predict models, we split all data into 10 folds and thus get 20 models in total by the two different network structure. Then we weighted sum all these models' output scores to make the final prediction. The weight of the contrastive learning and direct predict model is said to be 77% in total, and the weight of the MAE-based models is 23% in total. According to the test score, our model structure and method used last year has an improvement for 2.31% in terms of the F1 score, compared with the baseline model in 2021's competition. The new segmentation alignment strategy and the focal loss made an improvement for 0.04 and 0.05% respectively, and therefore our F1 score this year is 86.06%. For future work, since our model tends to predict more segmentations than the ground truth, we also consider setting different thresholds for the 23 groups mentioned above to control the number of boundaries predicted. It turns out that this dynamic threshold strategy can improve the F1 score on the valid set, but improvement on the test set is basically negligible. According to our analysis, the alignment strategy is formulated based on the inherent rules and data distributions of the dataset, so our adjustment accordingly will not cause overfitting. But the threshold selection of the model is more related to the score of the model output instead of the data distribution, and thus may lead to overfitting here. For future work, we consider training different models for videos with different number of segmentations. For example, after our first round prediction, videos with more than or less than 0.55 cuts per second can be divided into two groups to train two models respectively. Thus, we can encourage different models to have different sensitivities rather than simply applying different thresholds to the output of the same model. That's pretty much everything we want to present today. Thank you very much for your listening. Our code is available on our GitHub page, and feel free to contact us through email. Thank you.
Hello, thanks, Yuanxi. I think thanks for your interesting presentation, and I think a careful thought about the future works. So first, I think is there any live audience or in the chat room has some questions about this proposed methods? So I think maybe we can move on to the next one. Okay, thank you, Yuanxi, for your presentation. And next, we will welcome the winner of the second track to present their methods. It's from the Southern University of Science and Technology. Could you share the screen?
Yes, can you hear me?
Thank you, Yulong. I can hear you.
And can you see my screen?
Yeah, cool. I can see your screen. Yeah.
Okay, let's start. Hello, everyone. I'm Yulong Tang, an undergraduate student from Southern University of Science and Technology. In this talk, I will briefly introduce the technical details of our solution to generic event boundary captioning challenge 2023, namely LLMVA GEBC, large language model with video adapter for generic event boundary captioning. Our team members are all from SUSTech VIP lab. Generic event boundary captioning is a task aiming to generate 3 captions for the 10 boundaries caused by the status changes in videos. The 3 captions, one is describing the subjects of the events, while the other 2 are describing the status before and after the boundaries. And as we all know, in the past few months, large language models have been rapidly advancing and achieving good performance on a wide range of tasks of natural language generation. And they can take tasks like a sentence as input and generate its completion. Also, large language models are easy to transfer to multimodal tasks like video captioning and perform well. So we believe it's very promising that the large language model can benefits the generic event boundary captioning. So we hope it can take a video and boundary-aware prompt as input and output the compilation of captions. But the question is how to utilize the large language model to perform GBC task and how to represent the videos, how to adapt the video features to large language model, and how to obtain the video and boundary-aware prompts. So to answer the question, let me provide a overview of our proposed LLMVA GBC model and see how it addresses the question mentioned. Our model consists of multiple visual feature extractors, video Q-former adapters, and a large language model, OPT, and multiple visual feature extractors, including Bleep-Tooth image encoder with Q-former, Clip, and Omniverse are for extracting video representation. The video Q-former adapters is to transfer the dense visual features to sparse video query tokens. And the large language model, OPT, is for generating human-like and accurate event boundary captions. So to better exploit spatial temporal information, we use multiple pre-trained models to extract various visual features, including frame level and region level features. The used models are as follows. Bleep-Tooth image encoder with Q-former. It's pre-trained on 129 million images, and Clip pre-trained on 400 million web image test pairs, and Omniverse pre-trained on the ImageNet 22,000, and they are utilized to extract frame level features, where the features extracted by the Bleep-Tooth image encoder with Q-former are the primary features, while the other two are supplementary features. And to make bench processing easier, we apply an interpolation strategy to resize the temporal dimension to a fixed number. And additionally, we utilize the VNVL to extract region level features. The model has been pre-trained on 4 public data sets, COCO, OpenImage v5, Object 365, and the Visual Genome. And to obtain sparse video representation, the extracted visual features will be used to generate video query tokens. Firstly, the learnable positional encoding will be added to the extracted visual feature to provide the positional information for each feature. And then we should also provide positional information for the given boundary, namely boundary embedding. The boundary embedding vectors will be produced from the 10 boxes of the boundaries by normalizing them to 0 to 1 and feeding them to an inverse sigmoid function. And then the boundary embedding will be added to the precision encoded visual features. The visual features that has been both precision encoded and boundary encoded will be fed into the video Q-former initialized by the weights pre-trained on the web vid 2 million dataset by Video Llama. The video Q-former is actually a transformer decoder which performs cross-attention between the visual features and it initializes the query tokens to generate sparse video query tokens. And the next, to generate high quality captions, we adopt the pre-trained large language model, OPT. We first use the video query tokens to construct some prompts for the large language model. And specifically, we used a text token, video column as a prefix to tell the large language model the following are the information from the video, and the V is the query, the video query tokens, and they will be combined with the text tokens of a sentence like this video describes the A, and B is where the A can be subject, status before or status after, and the B is similar. Then we take the constructed prompt as the input of the large language model OPT to predict the completion. In other words, the event boundary caption for subject state before or state after, respectively. And in our experiments, we use the official provided full training set of kinetic GBC and train our model with cross entropy loss. When training, we freeze the large language model and only update the parameters of video Q-former. And here we list some experiments results. On the test set, our method achieved an average score of 76.14, which has 86% improvement compared with baseline method, and also outperformed the first place and the second place last year. So this demonstrates the capacity of the large language model on the GBC task. And here are also some captions generated by our model. As you can see, the captions for the subject status before and after are of high quality. And I think that is all. Thank you for your listening.
Thank you for your presentation. Is there any questions from the audience or from the chat room? Okay, I think your proposed work integrate a lot of very cutting-edge modules, both including some frame feature extractor and region-based extractor and large language model. I think it's quite intriguing to hear from your presentation, and I think thank you for your talks. And I think we can move on to the next one. And thank you again.
Thank you.
So next, I think we will yes, let's welcome the first place award of the TrackSun winners to present their proposed methods. It's from the Hunan University and University of Central Florida team Tom Chen CTG. And let's welcome our invited talks of the winner. You can share the screen now.
Hi, can you hear me?
Yeah, cool. Okay,
can you see my screen?
Yeah, I can see your screen.
Okay.
Yeah.
Okay, so let's begin. Hi, I'm Tongjia, a MS student from Hunan University, and I'm very happy to have this chance to share our parallel function interaction dual-centric approach for LabVIEW workshop track 3. And this work was jointly carried out by Hunan University and the University of Central Florida. And let's start with the background. The objective of the AQTC task is to facilitate the learning of AI assistants from instructional videos, enabling them to guide users in a step-by-step manner. This year's AQTC challenge has introduced an additional 100 new question and answer pairs compared to the previous year. The AQTC task involves various input modalities, such as egocentric instructional videos, corresponding scripts, egocentric user view images, and step-by-step QA pairs. And next, I want to introduce our baseline method, the function-centric approach carried out in the last year's AQTC challenge. And the approach firstly segment videos and scripts into function clips and function paragraphs instead of frame or sentences to ensure the completeness of each step. And then grounding questions in a function set using a TF-IDF model instead of relying on a cross-attention mechanism proves to be more effective in scenarios with small-scale data. And next, I want to talk about the motivations of our approach. The first motivation of our approach is the crucial need for domain alignment between different modalities in the AQTC task. Initially, the baseline model employed a vision transformer as the visual encoder and XLNet as the textual encoder, with no alignment between the two. And to improve the alignment, we replaced the visual encoder with clip pre-trained VIT, resulting in a unidirectional alignment that yielded a 3% performance gain. And furthermore, by replacing both sides of the model with blip, which provides bidirectional alignment, we achieved an additional 4% performance gain. And the second motivation is obtaining a video feature via pulling frame level features may harm the perception of interaction. And we can see from the video that in certain sections of the video where there is no interaction between the hand and object, the frames are just illustration of the object. And pulling the frame level features in these instances may diffuse the model's attention towards the hand-object interaction. So the last motivation is to model the global temporal cues can benefit the process of affordance grounding. And in addition to using an image model to capture local affordance, a pre-trained egocentric video text model, EgoVLP, is employed to capture global temporal information. And through large-scale egocentric contrastive learning, the model is capable of capturing global interaction contexts. And next, I would like to provide a brief introduction to our methods and present our results. So let me introduce the hand-object interaction aggregation module. In order to better capture the hand-object interaction information in long videos, we employ an off-the-shelf HOI detector, HOI RCNN, that demonstrates the states of hand-object interaction. And this is the illustration of the HOI aggregation module. And we first utilized the off-the-shelf HOI detector to process the video paragraph clips and obtain HOI states at the frame level. And it is worth noting that -1 denotes the absence of a hand in the frame, and 0 denotes no interaction, and 1 denotes the presence of hand-object interaction. And next, based on the frame level HOI states, we calculate the softmax probabilities within the current video paragraph clips. And lastly, we perform a weighted combination within the current video clip. And in this way, we obtain the HOI aggregated video features. So the ablation study provides evidence that our HOI aggregation module contributes to the improvement of affordance grounding. We trained multiple models using the features extracted by several well-aligned encoders, including Blip, Cliff, and EgoVLP. And by combining the results of all models through the linear ensemble, we obtained the final result. And the ensemble result achieved approximately a 4% higher compared to the best performing single model. And our approach ranked first in this year's AQTC challenge. And lastly, I will discuss the conclusion and future prospects of our work. So our work highlights the importance of using well-aligned visual and textual encoders for improved affordance grounding. And furthermore, we introduced the hand-object interaction aggregation module, which enhances the model's ability to capture interaction contexts. And additionally, we utilize the EgoVLP to exploit the specific characteristics of egocentric instructional videos in the AQTC task. And the future prospects of our research involve further exploring the context reasoning ability of large language models for the AQTC task. And there have been several works exploring related tasks such as AssistGPT, vlog, video chat, etc. And so that's all for my presentation, and thank you for listening.
Okay, thank you. Thank you for interesting presentation. And it's quite interesting to use EaGoVLP and I think human object interaction aggregation module in the AQDC challenge. I think is achieves a very promising results. So is there any question from the audience or chat room? Let me check. Okay, I think we can let's move on to the next part, and thank you for your presentation again.
Okay, thank you. Thank you.
Thank you. And as next part, we will invite the first place award of the guest track, cross-modal video retrieval with reading comprehension, to present their methods. Can you hear me? You can share the screen.
Okay, and I will share my screen.
Okay, thank you. You can start after you finish the screen sharing.
Okay, and I will start. Hello, everyone. My name is Zhao Yuxuan, and I'm honored to.
Okay, would you mind to share the full screen? I think it's still in.
I have shared the full screen.
I mean, use the presentation mode. We can still see you other sides under the window of the PPT. Or if it's hard to do it, maybe you can just start. It doesn't matter.
Okay, I will share again.
Oh yeah. Yeah, I think it's cool to.
There are some problem, and I will check it.
Okay, cool. That works. You can start your presentation now. Thank you.
Okay, sorry for the problem, and I will start now. Hello everyone, my name is Zhao Yuxuan. I'm honored to report our method on guest track. Our team member also include Chen Baoliang, Xu Yiqiang, Liu Fang, and Jiao Licheng. We are from the key library of intelligent perception and image understanding. My presentation today has 4 seconds, including background, dataset, method, and result. As mentioned by the previous person, long-form video understanding and generation is a challenging and important task in computer vision and multimodal. It has many particular applications such as video summarization, video caption, video question answering, and so on. These applications can benefit various domains such as entertainment, education, journalism, security, and social media. And cross-modal video retrieval and reading comprehension is a task that aims to search for relevant videos based on natural language queries that involve both visual and textual information. There are some challenges for this task. First is to need recognize and understand the text information in the video, such as saying text, captions, text, and connect it into visual content. Second is to need read and understand the query statement, analyze its semantic and logic, and determine which text information is important for video retrieval. The third is need to design effective cross-modal islands to matching categories to recognize the similarity calculation between video and statement. The final is to deal with the diversity and the complexity between videos and the statement. For example, the length, style, and the feel of the video, as well as the expression of the sentence, metaphor, and the reference. The dataset for this challenge consists of 10.5 thousand video and 42.2 thousand sentences, covering 8 scenarios such as activities, cooking, driving, and so on. This image is an example of the dataset. It's a video of basketball game corresponding to 4 sentences describing the video. And the purple part of the sentence with the underline is the text content involved in the video. And our final task is to match in the 2,727 sentence and video, calculate the similarity between each of them, and get a similarity metric. This is a simple diagram of the approach we took. We call our method as cross-modal video retrieval assist with image text matching. We use 2 models, StarVR and Clip, to produce text matching results at the video level and the image level respectively, and finally carry out multi-level weighted fusion of the 2 results. Next, I will describe our approach in more detail. First, I will introduce the StarVR model. It is a seeing text-aware video retrieval model consisting of 4 parts. For a video, it is first divided into space-time patches. Here, K represents the time dimension and L represents the space dimension, and then adding temperature and spatial positional embedding. The visual information of the video in time and space will encoded in this green encoder. Next, do OCR of the video, and the result is the set of T. Each T contains the recognition text content and the bounding box and the time of the text. The bounding box and the time information in this token will encoded by this yellow encoder, and the text information will be encoded by this orange encoder. The third part is encoding of the caption, which is same as the orange part, and the encoder of the fourth part use multi-height self-attention layer to fuse the vision and the textual features of the video in time and space. Finally, the output in Part 3 and Part 4 adopt a contrastive learning approach to learn the relationship between the video and the caption. This table shows the configuration we used to train this model, including the data argumentation we used. Although the video data has more abundant sense information and temperature information, our training data is limited. The text information and the video description in training videos are only a small subset of natural language. Therefore, we use CLIP, a large-scale image-text pairing pre-trained model, to assist video text retrieval and understand in testing phase. It starts by collecting about 400 million image text pair of data from the internet. And then A multimodal neural network model, including image encoder and text encoder, is used to map image and text into a common latent space, respectively. Finally, use constructive learning. The model is trained to predict which image and text are matched and which are not. In this way, clip learning, rich and diverse visual conception from neural network, neural language, and is able to transfer downstream computer vision tasks, their shot without any dataset-specific training. Therefore, we use multiple pre-trained clip models with different configuration to directly predict, including VIT-B and VIT-L. This is our final result, and we will upload our code to this GitHub link. Thanks for listening.
Thank you for the presentation. I think it's quite cool to provide text space-time encoders, and you pre-training contrastive learning framework for pre-training the multimodal information. And is there any questions for the audience? Oh, could you please let's go here too.
Actually, my question is, so what's the size of your L and what's your resolution of your video? Do they have the same resolution, temporal resolution with the text?
Sorry, can you ask again?
So you have the transformer. You are the image. You are the I times L. What's the size of your L? How many seconds?
VIT-L means we use the VIT large, and VIT-B means we use the.
But you have a temporal size, right, for the clip. What's your clip size? For the video, or you just do the image? You didn't do the video.
We just put only one image of a video.
Okay. Okay. So I guess I misunderstood what you did. Okay, thank you.
Thanks.
Okay, thank you for your presentation. I think for the next part, we will introduce Forrest. He will present the more details of track 4, which is video editing. So let's welcome Forrest for their wonderful talk.
Okay, full screen or? Hoping the remote people can see. You think it's okay? Good. Okay, let's get started. I guess I want to thank the other organizers of. Is there a problem? Okay. Sorry. Oh, there's one more thing. Yeah, cool. I see. Let's try that again. So yeah, I'd like to thank the other organizers of this track, as well as the 5 teams who submitted really interesting results to this part of the workshop. And in this short talk here, I'd like to introduce what is text-guided video editing, maybe hype it up a little bit, and show you where it fits in the general picture of generative AI for video video stuff. So let me just show some examples so you can get the gist. So if you're making a text-guided video editing model, and you may be familiar with this with commercial products like Runway ML, here we're doing more of the research component of this work. You get a few different things as input. You get this input video of some goldfish swimming, and you get the caption, several goldfish swim in a tank, sort of as just a reference for what the original video contains. And then you get another caption that's modified that says several sharks swim in a tank. And the task is to take the goldfish video and turn it into sharks. At least that's this particular example. And this slide here is using a method called tune a video, which is created by some of the organizers of this workshop and is one of the best open source methods out there for this capability. And as you can see, it's turned the goldfish into shark. So that's pretty good. I'll show a few more of these so you get the idea. So this is changing an object into a different object. You can also change the style. So this is taking a boat that's going on the sea and turning it into a 2D vector art style. I think this has worked pretty well also. Here's one where we start out with somebody surfing and we're kind of changing the background to look like Aurora Borealis, which I don't think could be done in real life, but generative AI is pretty smart and it's able to do this. So these are kind of some cherry-picked examples where the baseline, and we're using tune a video as a baseline for this challenge, does a pretty good job. But I also want to show that it doesn't always work. So there are many failure cases, which is why we wanted to bring researchers together to try to work on these failure cases and come up with better technologies. So here's one, in image generation, like with Midjourney, people love to do like a horse on a moon being ridden by an astronaut. We tried to do something like that here, where we gave the model a horse being ridden by a person, and we said put it on Mars, and it really doesn't know what to do. There's like a horse occasionally that flickers in, but it pretty much didn't work. Here's one where we said take this car drifting on the racetrack, make it neon light style, and the model understands what neon lights are, but it makes it all blurred and ugly and doesn't really work. So there's clearly a lot left to do to make this technology work well. But the question is, how do we measure progress in this field? And I looked at how other recent papers evaluate themselves. And what I noticed is they each have a different data set. Maybe a few YouTube videos, maybe a few videos pulled from a data set called Davis, which was originally for semantic segmentation, but you can just use it for this task as well. Yeah, no real consensus on data set. You can imagine if you're working on object detection, you came to CVPR, you go see all the posters and everybody has a different data set, you have no idea who's doing better. So we wanted to try to solve that problem. We noticed some patterns here. The data sets are pretty small. And I think the reason for that is because it's useful to have humans evaluate. Basically, human labelers look at videos and rate them, because the automated metrics are not very good yet, which is why these data sets stay small. And so we decided to create our own data set called LoveU-TGVE. We got 76 videos. Again, we kept it small so human labeling is possible on a reasonable budget. All have pretty open licenses, so you can modify and share the videos. The data comes from the same kind of sources as other papers use. And we kept the videos pretty small and pretty short. I know this is a long form video understanding workshop, but honestly, video generation still only really works well for short videos. And video editing only works well for short. So we started there. Maybe a couple of years from now, we'll have longer and bigger videos, hopefully, as well. So I want to show you now how we evaluate. So I mentioned we have 5 teams who submitted. How did we find out which is the best? Well, we put side by side the tune a video baseline with the new proposed method video, and we asked the labelers 3 questions. We said, which one better matches the caption? Which better preserves the original video? We also showed them the original video. And then aesthetically, which is better? So for me, if I were a labeler, I would say, honestly, the right one is winning on all 3 for me. I think it does better. It's still flickery. The numbers on this guy's jersey keep changing. There's a lot of work on temporal consistency to be done, but I think this is better than the baseline. Now I want to show some results. So these are the 5 teams. We're showing kind of what we call the win rate versus tune a video. So what fraction of the time does this proposed new model is preferred by the human labelers? And so the final metric we use for crowning the winner is the mean of these three things. And so we can see actually 2 teams, Camp and T2I Hero, have advanced for the state of the art beyond what the baseline model looks like, which is really exciting. We're making some progress here. And I want to go through, you know, a little more on the winners. So CAMP, which also won some of the other challenges here, from Tencent and Tsinghua, you know, 59% of the time the labelers prefer their work, so that's really good. T2I Hero also did a bit better than the baseline, pretty exciting. It's just, I think, one person who submitted this work, so good job. And then Noah Wukong, they did pretty close to the baseline. You know, not quite, but it's great to see so many people working on this problem and trying different approaches. And I want to show a couple examples of where the new models are winning. So remember I showed you this horse sort of mistake that didn't work with the baseline model. Here's the CAMP model doing the horse, and it's, you know, the lighting changes and it's not perfect, but there's definitely a horse. The ground definitely looks like Mars. I think it's an improvement, and next year hopefully be even better. Here's that racetrack one where the baseline model did the neon, but it made it all blurry. And here CAMP actually preserves more of the structure of the original video and also adds neon. So this, to wrap up my portion of this before I hand it over to the real heroes who actually did the work with submitting results, just to wrap up, we made a new data set. We got 5 teams who submitted their results. 2 teams beat the baseline. And I'll take some questions now, but then the next talk will be from Team CAMP. And then we'll have a couple more talks, one from another team who submitted, and then a couple of invited talks on recent methods for this task. But first, are there any questions? Do you want to come up here and talk into this mic? So let me see. Yeah, you want to just
yeah, hi Forrest. Thanks for creating this exciting benchmark. So my question is, so currently you are using human evaluation, right? So my first question is, how much does it take to do the evaluation? The second question is, if like more and more people coming into this field, so how can you do it at scale? You cannot like pay like hundreds of bucks for evaluation each time. So what do you think of the quantitative metric for the evaluation?
Yeah, that's a good question. So the human evaluation was actually relatively inexpensive. I think for the whole challenge we spent less than $5,000. You know, we tried to also pay the labelers a living wage if possible. But yeah, you're right. Like basically, human labeling is not free. It's far more expensive than computing automated metrics. And so then the question is, how do we develop automated metrics that would work better? So I think what I've noticed is whatever the image generation community does, the video generation community takes that and then tries to apply it to video. The image generation community may be a little further along. They have something called an aesthetic score, which is sort of a fine-tuned clip score, but you know, trying to understand human preference. And there have been some experiments. We even tried using one of those metrics here for kind of aesthetic score for videos. And so far, it seems kind of not super well correlated with what the human labelers in our, you know, that we used for final results have. But I'm hopeful that like as we get more and more human labeled data, we'll be able to kind of like pour that into producing a better metric that maybe then requires less human labeling in the future. Thank you. Do I have to check on the chat if there's any? Is there a way to do that? Okay, cool. Okay, so with that, I'd like to hand it over to Rui He. I'll stop sharing now, and they can grab the screen share.
Well, can you hear me and see my size?
Yes.
Okay.
Good.
Okay, thank you. Hello, everyone. I'm Rui He from Tencent. I'm very glad to represent my team CAMP to share our approach for the TGVE competition. Okay, let's start. First of all, I'll give a brief introduction to our competition task. TGVE task requires us to edit 76 videos according to the different given prompts. The edited videos were evaluated by humans following 3 criteria: test alignment, structure, and quality. As shown below, these prompts contain 4 types of changes, including object, style, background, and multiple changes coexist. The first row of this figure shows the original input videos, and the second row is a baseline algorithm tune of videos outputs. For example, in the first column, we need to change the object red roses to rainbow roses. We can say that the baseline did well in this example. The remaining columns show the other 3 kinds of changes. As we can say, the baseline cannot let these swarms in the third column glide underwater near a coral reef. And this panda in the final column is more like doing yoga by the lake rather than by the swimming pool as we want. Okay, let's go to the initial motivation part. As we know, the baseline tune a video algorithm is a one-shot method to deal with video editing. So a very straightforward idea is to do few-shot training by training the model on all 76 original TGVE videos. We expected that more training data will allow the model to be more powerful and learn more concepts from other videos to improve model editing capabilities. In the training process of the tune of video algorithm, only the attention layer parameters are updated, and we tried the same way to do few-shot training. What's more, because the few-shot training set is much larger than the one-shot method, we also tried to update all UNet parameters during training. The edited outputs by the 2 ways of few-shot are shown as the last 2 rows on the right. As the figure shows, the few-shot method doesn't work. The structure and the quality are far inferior to the baseline. So why does few-shot not work? We think it is because of the following 2 reasons. Our expectation of the few-shots is to learn more concepts from the whole TGVE videos. However, most useful concepts don't exist in TGVE original videos, such as coral reef and chocolate. Moreover, the data from other videos can cause interference, leading to the edited chaotic video structure. Therefore, we believe that our model must learn useful concepts in other ways. According to this motivation, we developed a 2-stage video editing framework. This is the stage 1 pipeline. First, we merged several popular T2I base models and get the general base model. Then, we fine-tune the general base model by 76 video frames and get the stage 1 model. Combining ControlNet, LoRa, and some other methods, we generate stage 1 outputs by the general base model and the stage 1 model. Okay, now why do we design the stage 1 pipelines that I just described? First, we merge the base models because different base T2I models are good at different concepts, like the MENA model we used is excel at animation style. Merging these base models means we merged concepts that different base model excels at. Then, during fine-tuning our base model, we proposed a customized prompts design. As shown here, we added CVPR 2023 TGVE and the frame sequence ID, like frame 001, frame 002, to each frame's prompts. We believe this design can add more prior knowledge to prompts. It is easier for our model to preserve the structure of the input videos. What's more, as we know, LoRa is very effective for style changes, so we use the ready-made LoRa or train LoRa by ourselves to generate specific style videos, such as Van Gogh and Leon styles as shown here. Just like LoRa for style editing, we combine segment annexing and open clip to deal with object or background editing. Just like the example here, we need to change the goldfish to sharks. We use SAM to get some masks and use open clip to choose which mask is our target goldfish. In this way, we could distinguish the object from the background in the original videos, and then we could edit the background and then we can edit background or objects separately. Overall, we use the strategy above to produce many well-generated concepts that don't exist in TGVE impulse videos. These generated videos will be added into training dataset in stage 2. Let's continue to stage 2 pipeline. In this stage, we broaden our training dataset by adding stage 1 outputs, reminding again that these outputs contain many well-generated useful concepts, besides some MSVD data, which contains related concepts, are also added to our dataset. Then we fine-tune the stage 1 model by the enlarged dataset and get a stage 2 model. We use the stage 2 model to generate the final outputs. During the stage 2 generation process, we use a multi-frame video rendering method to ensure video frame consistency. After introducing our two-stage pipelines, we can have a brief comparison between outputs from stage 1 and stage 2. In the cat judo example in the first column, the cat from stage 2 is clearer and the background is more stable. The squirrel climbing example in the second column shows that the Van Gogh style is better restored, and the lost squirrel in the stage 1 output reappeared in the stage 2 output. In addition, since we did data cleaning for the training data of stage 2, some unreasonable image structures in stage 1 no longer appeared, such as the fireworks on the ground in the third column and the frequent switching between cat and dog as shown in the last column. There are more results shown here. If you still remember the generation results by baseline as I showed at the very beginning, please look at the videos framed by me with the red boxes. Compared to the baseline, the panda here is doing yoga near a swimming pool, and the sword appears underwater near a coral reef, which are both edits that cannot be implemented in the baseline method. At last, let me make a summary of our approach. We propose a two-stage video editing framework. Stage 1 generates relatively weak outputs, which were used as a part of training dataset in stage 2. By merging base models, LoRa, SAM, plus OpenClip, and other methods, our model learned more useful concepts, which improve the test alignment of the edited videos. By our designed prompts in fine-tuning process, the structure of original videos can be well preserved. By the multi-frame video rendering method, the consistency of video frames can be well ensured. Finally, we won the TGVE competition by 0.591 on human evaluated average scores. The test alignment and quality score achieved first place, and the structure score achieved second place. The specific scores are shown in the table below. Well, that's all I want to share today. If you want to know more details, feel free to contact us through email. Thank you very much for your attention.
Would anybody like to come up and ask a question?
Hey, thanks for the great work and great talk. Could you elaborate more on the details of multi-frame rendering? I think you mentioned that, but I don't know whether you are using your own method or it's a already existing method. Thanks.
Well, it's already existing methods, and I can have a brief introduction of multi-frame rendering. Multi-frame rendering is a way to improve the consistency of frames when generating frames with generative videos. Essentially, it's an application of image-to-image imprinting. It stitches together the first video frame, the previous frame, and the mask error in which the last video frame will be generated. In this way, model can learn the structure of the first frame and the previous frame, just like the spatial temporal attention in tune-up video. So multi-frame rendering, I think, is helpful for video frame consistency. So we use this way to generate our videos. I hope my answer can answer your question.
Yes, thanks. Yeah, good answer.
Okay.
Okay, thanks. So let's move on to the next speaker. And I think it's Tianyi Lu. So yeah, if Ray, if you could stop sharing your screen, please, and then we'll move on. Could you okay, perfect. All right, and yeah, Tianyi, would you be able to start? Okay, perfect.
Hello, can you see my screen?
Yes, everything looks good, and please get started.
Okay. Hello, everyone. My name is Tianyi Lu, a master student at Fudan University and also an intern at Huawei NOAA's Arc Lab. It's my honor to present our method of the text-guided video editing task, fusing latents of diffusion models for multi-range video editing. The presentation consists of 4 parts. Let's begin with the background. The TGV task aims to enable the model to edit the video with a target prompt. For instance, given a video of a jeep car is moving on the road, the model will edit the video to a jeep car is moving on the road cartoon style. And the dataset consists of 76 videos. Each video has 4 editing prompts. Since there is still no publicly available base model for high-quality text-to-video generation, and existing works such as cog video and text-to-video synthesis models from Model Scope are either suffering from poor temporal consistency or watermarks. A high-quality base video diffusion model is required for text-to-video editing. Following Stable Diffusion, we introduce a video diffusion model trained with weights loaded from Stable Diffusion. This is the architecture of our model. In detail, we inflate the 2D ResNet blocks to 3D ResNet blocks in UNet structure following to a video. In order to increase temporal consistency, we add 3D convolutional layers and temporal attention layers in UNet. For efficient training, the parameters of text encoder and ResNet are frozen after loading the weights from Stable Diffusion. For training our VDM, we sample 8 frames from a video with a temporal stride of 4 and use a spatial resolution of 256. The training objective is MSE loss between input latents and denoiser latents. For achieving better generalizability of VDM, a probability of 10% is set to randomly omitting the input video caption. Training dataset is very important for acquiring a high-quality base video diffusion model. Unfortunately, existing video datasets with dense captions are neither high quality nor diverse enough. To this end, we first collect large-scale high-quality video datasets for base model training, which are mainly from 3 sources. The first is video datasets with captions. TGIF and VTEX are 2 video datasets containing trimmed videos with captions. To ensure the alignment between videos and captions, we only take videos with a duration of less than 10 seconds from WebVid 10 million. Also, since most videos in WebVid 10 million are watermarked, we use OpenCV to remove the watermarks for improving video quality. The second is video recognition datasets. In order to increase the variety of video topics, we also use Kinetics 700 video recognition dataset and apply a video captioner model, Blip V2, to generate captions for each video. We randomly sample frames from a video and obtain captions for each video frame. The third is the image dataset. To strengthen the alignment between visual and textual modalities, we extend the Lion 400 million dataset to be a video dataset. Through random zooming and panning, a video can be generated from a single static image. Since the fine-tuned VDM may generate videos with low frame consistency and diversity, we introduce an image stable diffusion model and fuse the latents from both video diffusion model and image diffusion model. This picture depicts our pipeline of video editing. In the first stage, we fine-tune our base video diffusion model with a raw video to be edited for better fidelity. The fine-tune process follows tune of video and only a few parameters from UNet are trainable. In every inference step, The denoise latent from the fine-tuned base model is denoted by epsilon base, and the output from Stable Diffusion is denoted by epsilon SD. We apply latent fusion for combining the latents from these two diffusion models and obtain mixed denoise latents as following formula. The high parameter alpha controls the extent to which the static appearance is kept. A larger alpha makes individual video frames look better, but does harm to the temporal consistency. In practice, we set alpha to 0.5 in our experiments. We compare our FLDM with tune video baseline on both short-range and long-range video datasets. We try 3 combinations. The single use of VDM provides better text alignment but lower frame consistency. When we use VDM combined with control net with depth condition, the frame consistency remains low as well. And then we apply latent fusion to Stable Diffusion and our VDM, we get better frame consistency. This is a display of some of the results obtained from the 4 methods. Compared to tune a video baseline, our video diffusion model and FLDM achieve better temporal consistency. We can see that videos edited by FLDM have smoother frames. In conclusion, our technique contributions are summarized as follows. Firstly, we collect large-scale image and video datasets for training a video diffusion model and apply a series of pre-processing methods to obtain high-quality training data. Secondly, we provide a high-quality video diffusion-based model for one-shot training framework. Collectivity experimental results show our video diffusion-based model is superior to the video baseline by a clear margin. Then we fuse denoise latents from both image and video diffusion models during the inference stage. Such simple yet effective strategy can achieve better temporal consistency among video frames. That's all for my presentation. Thanks for listening.
Great presentation. Are there any questions in the room here? Anyone want to come up and ask a question? I don't see any questions in the chat either. So let's see, is Chanyan Chi here in the room? Okay, do you want to come up? We have a little bit of flex time in the schedule, so maybe take a couple minutes to get IT set up here.
So would you rather send him the slides because I'm not doing it, or would you rather look at the slide? Yeah. Oh, you're already in, okay. Yeah. Let's go with that one. Yeah, if you want to go a little, if you feel like going a little over, we're actually ahead of time right now. Oh, I mean, there is a break, but I kind of assumed that everything would run, right? So, yeah, I kind of don't want to send everyone away and I want to come back.
Thanks for the introduction from Forrest. Hello, everyone. I am Chen Yangqi from HKUST. Today, I'm happy to share our recent work, Fit Zero. It's a work done during my internship at Tencent AI Lab, and this work is supervised by Xiaodong Cun and Qifeng Chen. So let me first introduce the target and the task setting of our project. So given a source video with multiple frames, the user provides a source prompt to describe the objects in the source video and an editing target prompt to describe the attempt of editing. So our algorithm produces a consistent video that is aligned with the target editing prompt and preserve other geometry and temporal motion in the source video. So we consider 3 types of editing in our method. The first one is the global style editing, and the local attribute editing, and the object shape editing. So let's first go through our result demo. The first part is the global style editing. We add new styles to a real video and preserve the temporal motion and the most geometry in the video. Also, we add a little style geometry and a new color tone to the video. So we can add the painting such as Monet style. And the second one is local attribute editing. We added the texture, the material of the object in the video while preserve the overall geometry. So, and we preserve the other words that are not edited to the source video. And we can also add this background such as flow to grass. And we also support multiple object editing. Here, the source video is a squirrel eating carrot, and we generate a rabbit eating eggplant, a mouse eating peanut. The final part is the shape editing result. So this part is a little difficult. We can generate an object with smaller or larger size, and we can also generate the new human characters while preserve the pose in the source video. Okay, so let's discuss the challenges in the video editing. Our work is inspired by Tuna Video from Show Lab in the December 2022. It's a dream booth-like overfitting method. So the core design is to inflate the 2D self-attention to the spatial temporal self-attention and then fine-tuning on a single video. So the challenges of this method is that for a complicated video, it is still very difficult to overfit the exactly temporal motion, only use the model weights. And such unstable overfitting will take longer time and much deep disk space to save the model weights for each source video. There are some concurrent work in the community, mostly published in March of 2023, such as video P2P, edit a video, and video to video zero. So this method extends the image editing method, the null text inversion and prompt to prompt to the video version. So this method fine-tuning text embedding for all frames of the video, while our concern is that the text cannot correctly describe the spatial layout and temporal correspondence because the weight of the text embedding doesn't have a temporal dimension, and the stable diffusion is pre-trained on the image data set. It has a little value about the temporal correspondence. So fine-tuning based the inversion method also takes times and more hyperparameters. So in contrast, we propose a zero-shot video editing, just use the weight of stable diffusion. We inherit the inflated temporal unit from Tuna Video. So in each frame at the denoising, we query the features in the key frame to preserve the content consistency between different frames. And we propose a novel coupled inversion and editing pipeline. We first extract the representation of motion and geometry during the inversion. Then during the denoising, we maintain the motion similarity between the editing results with the source video. So This is the animation of our method. Given a source video with multiple frames, we first conduct the DDIM inversion pipeline. In the time step of the DDIM inversion, we save the attention maps of spatial temporal self-attention and cross-attention maps, denoted as SA and CA here. So in the last denoising time step T, we can obtain the inverted latence, which contains other informations. So during denoising, we start from the inverted latence, go back to the RGB video. In each time step, we fuse the attention maps with the same time step during the inversion. The right part shows the details of our attention blending block. Sorry. So for cross attention, we inherit to designs in prompt to prompt. We replace the words that not edited, such as the countryside background here, during the denoising with the maps during the inversion to maintain the semantic layout of the background. And for the words such as the silver jeep that we want to edit, we just preserve the layout during the denoising. So for the self-attention, we propose a self-attention blending strategy. We first obtain a binary mask from the cross-attention map, and then blend the self-attention using the mask. We will introduce the blending strategy later. So to validate the effectiveness of our inversion attention, we begin from two examples of zero-shot image editing from a cat to a tiger. The upper part is the reconstruction attention guidance from previous work. So here the inversion and the editing part are decoupled. So these methods, such as prompt to prompt, first obtain noisy latence during the DDIM inversion. Then two parallel branch of reconstruction and editing are conducted concurrently. So we can see that the cross-attention map during reconstruction is not accurate to capture the pose of the cat. So such reconstruction attention guidance method cannot generate the tiger with correct pose, and the background is not preserved. So in contrast, we propose the inversion attention method. We just use the attention map during inversion, which is very accurate to preserve the pose of the cat, because it doesn't have the problem of large classifier-free guidance and limited DDIM steps problem. So our method is accurate enough to generate a high-quality tiger just in zero shot. So for shape editing, it can be more challenging because in the temporal dimension, the shape is coupled with the motion, which is not learned by a text-to-image stable diffusion model. So our design also use the fine-tuning strategy from Tuna Video to fine-tune stable diffusion on source video using low-rank convolution and regularization loss, similar to DreamBoost. Our novelty is to propose the spatial blending strategy for the spatial temporal self-attention maps to preserve more details. So let's go deep into this self-attention blending strategy. The left is our technical design illustration, and the right is our application study. So for previous methods such as prompt to prompt, they replace the full resolution self-attention maps without a mask. We can see that in the last column, the color and the shape of editing result is still similar to the input silver in the source video, because the self-attention maps is decayed to the editing results. So during our self-attention blending, we first obtain a binary mask using the editing words, the Jeep here. We threshold the cross attention to obtain this mask. Then in the blending, we first reutilize the self-attention map during the inversion. So in the editing pixels, we use the attention generated during the denoising, while for unrelated pixels in the background, we use the self-attention during the inversion. In this way, we can preserve the geometry and the motion of the background while generating new shape in the foreground. So we can see that use these designs, the color and the shape is correctly generated as a post shake. Okay, so this blending strategy use the mask from the cross attention can be extended to the latent blending for better detail preservation. Here we implemented the latent blending similar to the previous self-attention one. We can see that the pixels in the background is identity to the input. And we also provide a quantitative comparison with previous work, includes frame-wise image editing, the neural layer atlas, and the Q1 video. Our method is the best in user study and temporal consistency evaluated by clip matrix. And our method is second in the frame accuracy. Thanks for your interest. Please check more details in our project website. So that's the end of our presentation.
You can stay here for a minute. Does anybody want to come up and ask a question? No questions here. And oh, do you want to come over and grab the microphone?
Thank you, Chen-Yang, for your exciting work. So basically, my question is: so your work is very good at style transfer or attribute editing, but for like shape editing, you have to fine tune a model, right? So like tune video. So my question is: do you think it's possible that we can propose some like training-free approach to do the not shape editing? Like yeah, we don't have to train the model, just use the original model and propose some training-free methods to do the shape editing. Yeah.
Yeah, I think so. Basically, if the object is static in the video, it is possible to do shape editing. There are some works like make it 3D and 0, 1, 2, 3 show that the Stable Diffusion have knowledge of 3D objects. But I feel if you require some deformation such as human pose in the video, it's very difficult to generate just use Stable Diffusion. It's a better strategy is to use a specific model in the pose and 3D area to enhance the capacity of the Stable Diffusion. Yeah. Any questions?
Hello, can you hear me?
Yeah.
Hi. Thanks for releasing this great work. I'm very interested in how you blending the. I see one of your slides is about latent blending. Could you give me more details about how you conduct latent blending? Yeah.
Okay, so latent blending is actually a part of the code is implemented in the prompt to prompt, and there are some also methods like blended diffusion. They have achieved that it's possible to generate to preserve more details by latent blending. So we just use the masks during the inversion stage. We can maybe I can share the screen for better illustration. So here we store the attention of editing words, the silver drip here, and use a threshold to generate a binary mask. So using this mask, we know which pixels we want to preserve and which pixels we want to generate during the denoising stage. And in the each time step of denoising stage, we can replace the latents at a pixel that we want to preserve with the latents during the inversion stage. In this way, we can preserve the details of the source video. Yeah, just like that. It's similar to the self-attention blending, but the input is the latents, not the self-attention maps. Do you still have questions? Okay. Yeah.
Can you?
Thank you for the great talk. It's very impressive. I'm not sure if I quite get the blending idea or not, but the question is like, because so far like we have like foreground and background, we do this master blending, and in this case we are trying to have a different shape. So what if like we have a shape of like a square shaped of something, and then we have a round like the bowl shaped or something? Can we also do something similar to this mask blending idea? I mean, like for example, this is the car, and the shape is always like a car shape. But if we are going to replace it as a bicycle, so in the current baseline or even the control net style, it will not work.
Yeah, bicycle is very difficult because it's not the same category, and fine tuning will hurt the capacity of the model. Yeah, I think maybe you can use a regularization strategy. You can collect a bicycle data set, and during the tune video overfitting stage, you can iteratively fine tune on the bicycle data set to preserve the knowledge of bicycle, and use that trick and combine with the control net. I feel it's possible to achieve that result. Yeah.
So it will be like also a bicycle video data set, and then the foreground can be a bicycle mask.
Yeah.
Yeah, thanks for the very good job.
Very good. Okay, let's move on to the next one.
Okay, hello everyone. I'm Yingjing He from Hong Kong University of Science and Technology. Today I'm very excited to present our recent research on video generation, specifically on the topic of crafting your videos using unconditional and controllable video diffusion models.
Okay, great. So our final speaker today will be Yingjing He, who will talk about Video Crafter.
Yes. Hello, can you hear me? Hello.
Yeah, we can hear you.
Okay. Let me continue.
Okay, could you start from the beginning? Sorry, we just have some IT issues. So thank you.
Okay. Okay, I'm Yingjing He from Hong Kong University of Science and Technology. Today I'm very excited to present our recent research on video generation, specifically on the topic of crafting your videos using unconditional and controllable video diffusion models. For the unconditional model, It generates videos from pure noises without any specific guidance. Usually we study unconditional video generation in a specific domain like the sky, dynamics, or the human actions. In LVDM, which is our recent work, we achieved the state-of-the-art results on both short video generation and the challenging long video generation. And our models can generate videos of thousands of frames as shown here. However, generating random videos with no guidance is much more challenging than conditional generation. Besides, human cannot control the synthesis process in order to obtain the specific video contents as they want. Thus, we continue to explore controllable video diffusion models to facilitate various of controlling signals like text prompt, style, depth, and pose. The text prompt can provide a rough and abstract control over the video content, and we provide a text-to-video model in LVDM as an extension. And we inject various of personalized styles to the text-to-video model, like these 4 different styles in Video Crafter. For the depth and pose, they can inject more detailed layout and structure information to the model, which are complementary to the text prompt. So we also study these 2 modalities in Make Your Video and Follow Your Pose. Let's first take a look at unconditional video generation. The challenges here lie in 2 aspects. First, the video diffusion models of previous works take a large computational cost and require a very long training time. Second, they cannot generate very long videos because they suffer from the performance degradation problem when auto-regressively extending the generated video length. So to tackle these challenges, we propose a latent-based video diffusion models referred to LVDM. Specifically, we exploit a video autoencoder to compress the dimension of video data, and the diffusion and denoising process are performed in the latent space. We conduct the efficiency experiment compared with VDM and MCVD. LVDM is 6 times faster than VDM and 4 times faster than MCVD. Additionally, our model achieves much more better generation performance than them under the same training resources. And we make a further step towards the long video generation. And we observe that directly generating long videos autoregressively leads to severe performance degradation problems as shown in the previous slides. This is because the gap between the training and the autoregressive inference of the conditional frames. To overcome this problem, we propose a hierarchical LVDM model. During training, we train 2 models, including a prediction and an interpolation model. Both of these 2 models are jointly training with unconditional inputs and conditional inputs via the mask sampling. The joint training has 2 advantages. First, we can unconditional draw a clip via the prediction model and then extend itself using the same model. Second, the joint training facilitates the unconditional guidance during sampling, which we find that it helps to reduce the degradation issue because the unconditional score has no accumulated error, which exists in the conditional score. And we also perform diffusion on the video latence in the noise level S, and we use the binary mask to blend the conditional frame and the generated frames together. We refer this process to conditional latent perturbation. We observe that it also helps to reduce the degradation because the gap of generated condition and ground truth condition are reduced by the noise perturbation during both training and inference. Besides unconditional generation, we provide an extension to open domain generation and inject test controls. And we release our models on Video Crafter with 2 more applications, including personalized style control and depth control. Video Crafter is an open sourcing toolkit for text-to-video generation and editing. So for the style control, we insert new trainable linear layers to current linear layers in intention modules and optimize these residual parameters to encode the user-provided style. For the depth control, we train a depth adapter to map the depth condition to feature residual to control the generation. Our another work is Follow Your Pose, which aims to generating pose-controllable character videos, leveraging the pre-trained stable diffusion. The key challenge here is the lack of diverse character video dataset. So to overcome this, we utilize natural videos without characters, as well as diverse character images and their corresponding poses, termed as a line pose dataset. And we propose a two-stage training strategy and separate pose and temporal modules to learn from the two datasets. Specifically, we learn the pose alignment from the line pose, and we learn the temporal coherence from the general videos without poses. As a result, we can generate both spatially aligned and temporally coherent videos of diverse characters, and motion, including the single character and multiple character cases, and large motion cases. Make Your Video is also our most recent work, which aims to do the depth controllable text-to-video generation. It has better visual quality than the previous mentioned adapter-based depth control model in Video Crafter. It has better visual quality than the in this work, we leverage the pre-trained depth condition, the stable diffusion, and insert temporal modules for modeling motion dynamics. Specifically, we designed the spatial temporal residual block together with the temporal transformer. The design of the spatial and temporal residual block is based on the observation that there is a domain gap between the caption video dataset and the caption image dataset, which is used in the training of stable diffusion. Thus, inserting a spatial convolution before the 1D temporal convolution can help the domain shift and make the temporal learning more easily. Experimental results support our hypothesis that using the pseudo convolution improved the performance compared with using the 1D temporal convolution only. Besides, we propose causal attention masking during training and inference to facilitate long video inference. This is used to avoid the problem that more tokens participate in the temporal self-attention. The less attention is distributed to each token. So clumping the number of tokens within a maximum value can help both the temporal consistency and the visual quality when inference with longer lengths. Make Your Video enables various of applications, including the real-life scene-to-video, 3D scene-to-video, and video re-rendering. It is better than the Video Crafter, depth adapter, and tune video and text-to-video Zero. So in summary, we have talked about conditional video generation using VDM and controllable video generation via various controlling signals. So due to the time limit, I cannot cover all the details of our research. So if you have any questions or comments, you can also drop me an email or scan the WeChat QR code, and we can discuss them in detail. So that is all about my sharing, and thanks for your attention.
Thanks for your talk. Does anybody in the room here like to ask a question? You want to come up to the microphone, please?
Hi, Mr. It's not nice talk and great work sharing. And I'd like to know, I see you have two different strategies for long video generation. So what's the difference between the long video generation strategy in the LVDM and the make-your video? And things, which one is better for robust long video generation?
Okay. I think the two methods in LVDM and the macro video are complementary because in macro video, the training length of the video generation model is only like 16 frames, and during inference, it can use the same model to generate longer frames. But in LVDM, we actually trained two models to generate the frames in a hierarchical manner, and the synthesized video length is the same with the training length. So I think using the same model to inference more longer videos can only limit it to 64 frames, which is not longer enough. And in LVDM, combine the two models together, it can generate thousands of frames. Yes. But in practice, I think we can combine these techniques together for long video generation. Yes.
Oh, thanks.
Yeah, I guess not really better remarks, but just
Yeah.
want to
remote people.
okay, yeah.
Yeah, so thanks a lot for the talk. You can probably turn off the screen share and then we'll just go to the final remarks and then we'll go to lunch.
Yeah, so I guess nothing but just want to thank everyone for attending this workshop and hopefully you guys submit more submissions later on in our future editions, and looking forward really for us to work together to solve this challenging problem of long form video understanding and generation together. Yeah, thank you for being with us today.
Thank you.